हेलो हेलो।
हेलो हेलो। हाँ आयुष है। हेलो हेलो। ठीक है।
आपको एक ईमेल मिलेगा।
Yeah, no, it's on. Yep, definitely on.
चाहिए तो म्यूट कर, ये इधर बटन है म्यूट।
I did. Oh, there it is.
Okay. Same. As you can see, there are lots of words. As you can see, there are lots of words. As you can see, there are lots of words.
Okay, so first announce. So I'm Piyush from TFR, and the first announcement. There'll be a banquet at 7 p.m. The venue is listed in the online schedule already, and buses will leave from here at 6 p.m. Um, uh, hope everyone has noted that down. So the invited speaker for today, it's a pleasure to introduce Leonard Schulman from Caltech. So Leonard did his undergraduate and graduate studies at MIT, finishing his undergraduate degree in 88 and PhD in 92. He has worked in a variety of areas. It includes algorithms, geometry, quantum computation and information theory. So I just maybe mentioned two highlights. So along with Sanjay Das Gupta, he was one of the first people to analyze, one of the early results to analyze the expectation maximization algorithm. Theoretically, it's a very widely used heuristic, but theoretical analysis is usually not there. He's also been a pioneer in the field of interactive communication, which also won the Test of Time Award at Fox last year. Today he'll be talking about something different. He has been working on over the last few years. It's causal inference. So this is there should be a joke here, right? So this is like the problem of taking the dictum that correlation is not causation and trying to say that no, sometimes you can deduce causation from correlation in some cases. So it's understanding when you can do that. So that's what he'll be telling us today.
Is it broad? Yeah, sounds like it's broadcasting. Hi. Thank you, Piyush. Thank you very much to the organizers for inviting me. It's kind of exciting for me to come here and for their wonderful hospitality during the visit here. I'm going to do the following thing. So I think causal inference is a really interesting, certainly a very interesting question. I think it's one that the TCS, our field of theory of computing, it doesn't come from us. But it's kind of adjacent to a lot of things we're interested in, explaining data and so a few years ago I started getting interested in this, and I learned a little bit about the models and about the ifs and whys, and Piyush's introduction was very appropriate in terms of when can we say something. So I thought I would come here and I would try and deliver some of the introduction that maybe I could have benefited from when I started reading these things, and hopefully that will be helpful to someone. And so this talk is subtitled A Tale of Two Paradoxes. So I'm going to get to two paradoxes very soon. And so the first, just to give you an overview where we're going, the first section of the talk will be this discussion of these two paradoxes and what causality. And then without really talking about results, and then I'll get a little bit more formal about the models and results, and then I'll give kind of a very rapid and very biased overview in the sort of the latter part of the talk. And I'm very happy to be swayed in our use of time by questions and so forth. So okay, so let me begin with discussion of like what do we like to do in science? What's the ideal way of doing science? Is a randomized control trial. So this is often called the sort of gold standard of how you do causal inference. So you would like to do that, and that's how science has been done ever since like the sort of scientific method was kind of formulated as an experiment, or experimental science anyway. But there's tons and tons of times where this is just not available to us as a strategy. The most perhaps most obvious is there are ethical obstructions to doing experiments on human beings. Very sadly, despite those ethical, there have been various regimes have conducted experiments on human beings. I don't want to give the examples, but this line has been crossed on multiple times. But it's a very strong reason not to do that. But I thought by way of sort of as a more amusing example, I would show you the following newspaper clipping, which maybe 5 years ago, as marijuana started to become, I don't know if this has happened in India, but in America and in Europe, marijuana has become gradually semi-legalized, legalized, liberalized, and so the Canadian government, once unwilling to go anywhere, sort of near this, has sort of decided at some point that, well, okay, we have to understand, scientifically what's the effects actually of marijuana. It's of marijuana. It's unclear. There's not really scientific study because it was always just like this illegal thing. So will a pregnant mother, harm the baby if she uses this stuff? Does smoking the stuff affect driver's reaction time? And what threshold does the pot consumption become destructive? And so the right thing to do scientifically, if you know the scientific method, is you take a bunch of subjects, maybe a bunch of teenagers who've just got their driver's licenses, and you give them half of them, a good smoke, and the other half you give them something that smells like it but isn't it, I guess. I don't know exactly what the control would be. And you send them out in the roads. Okay, and you sort of, okay. Okay, this is a much more amusing example to talk about than anyway. So they didn't do this. I actually don't know what they did. So that's one reason you don't do randomized control experiments. There's a bunch of others, completely different. One is governance. For example, what ages should kids start first grade or start to learn to read, or what age is optimal for this? How do you do this kind of experiment? You tell Mr. and Mrs. Smith, your son is not going to start learning to read till 7, but he can already read. No, so some policies anyway are fixed, and scientists can't go in there and just do this, even though it might even be kind of arbitrary. But you just can't. You can't set those policies. Other reasons that the system that you're studying is unique. So one interesting example of that is, think about how the U.S. Federal Reserve Bank controls, interest rates. It's a lot in the news these days. It's actually always a lot in the news, but especially these days. And so you might say, okay, well, let's get as much data as we can. Let's look at all, there are what, 197 countries around the world, and most of them have their own currencies. And, we could look at how they set, could get maybe a much more, 200 times the amount of data that way. But you can't because, the US dollar is sort of special. And so you only have this one system, and you only have your own data, and it's just, you can't do an experiment. Another really much more serious example is what happens when you drive up CO2 concentrations in the environment. This is the experiment we're doing right now, but we don't have a control. This is a plot right over here. This is a plot of CO2 concentrations from 1960 to the present. They were steady. Before 1960, they were going to be a little bit lower, but it was almost steady for 800,000 years. And now we're giving it an impulse. And we're waiting to, actually, I don't know if it's just an impulse. Impulse dies out. I don't know what we're doing. I just know what we're doing. I just know this part. And we're going to, we'll find out, but we won't actually know we won't actually be able to do the cause and effect, because we didn't do the other experiment, and we don't have a twin Earth and so forth. So there are all these problems. So let me be a little bit slightly more rigorous about what we mean by a causal effect. So, and I'll start introducing graphs, because we'll be seeing graphs a lot in this talk, little graphs. And so here's a sample scenario that gives you like a little causal, gives you a little directed graph. Every variable corresponds to a vertex. So the variable might be, students have tests, and so we want to understand how much a student's preparation affects their, their exam performance. And the way one way of kind of modeling that is that essentially there's a noisy channel from an intervention variable. The intervention variable is how much the student studies for the exam, to a response variable. Does he pass? Does he fail? What his score is. And this is a noisy channel in the sense it's statistical. So when you study and sleep, you have 0.9 chance of passing. When you study but you don't sleep, you only have only 0.6. When you don't study at all, you have only 0.1 chance of passing. So you get this noise, information theory terms, you get a noisy channel. And this is what we'd actually like to understand, if we could, but we have to understand it from passively collected data. We can maybe monitor what the students did, but we can't tell them, Cindy, don't study. It doesn't work that way. So we want to kind of figure these things out from passive data. And the complication for us is that the graphs are going to be, they're going to be more complicated. They're not going to all just look like that. So before I get to those causal models, which I'll get to, I'm going to go back to sort of my talk strategy, which is just as Pierre said, which is just I'm trying to, why is correlation not causation? Let's try and be a little more, it's fine to say that, it's true, but like why? What's the obstructions? So to me, it's nicely captured. There are two obstructions, and they're nicely captured in two paradoxes, if you want to call them paradoxes. One's called Simpson's paradox. The other is called Bergson's paradox or bias or fallacy, depending who you are. And I think they're very instructive, and they're so instructive that I think this quote from Kierkegaard is very appropriate. He said, one must not think ill of the paradox, for the paradox, the passion of thought. It really makes you think. And the ultimate potentiation of every passion, which I would interpret like what does this paradox give me, is to will its own downfall. Like at the end of it, you actually understand something. It doesn't look like a paradox to you anymore. So this is, I think that's what he meant. Anyway, that's what I mean. So Simpson's paradox. This is actual data from a study in 1986. There was a hospital, and there were two patients come in with kidney stone to the hospital. I've seen this happen once before. It's intensely painful. The people, nurses will tell you that, big, strong truckers come in and crying like babies. It's an extremely painful thing to have. And so people arrive at the hospital. It's very easy to diagnose that what they have is kidney stone. And then the hospital, in this case, had two treatments, which we'll just call treatment A and treatment B. And this is, there were, treatment A was given to 350 patients, treatment B was given to 350 patients. And what we've plotted here on the sort of horizontal axis is the success rate with treatment A. Don't know how they define success, but it's okay as long as they define success for the same for both. People don't usually die from this, so I don't know what success was defined as, but as long as it's defined the same, we'll just, So the success rate was, and I don't remember what the number is here, but you can see it's sort of a little bit below 0.8, and over here it's more like 0.84 maybe. And good, so treatment B looks maybe a little bit better in this plot. But then when you have the kidney stones, you can figure out how big they are either by scanning or if you had to do them maybe by removing them. So they went a little deeper into the data, and they sort of classified the patients by whether they had small kidney stones. These are little accumulations of a hard rock-like substance in your system, and or where they had big kidney stones according to some measurement threshold. And then they find the following data, which is where the patients had small stones, this dot was to the right of the 45-degree angle, meaning there was a slightly higher success rate with treatment A than with treatment B. And strangely, the same thing was true for the patients with large kidney stones, that the success rate was slightly larger with treatment A than with treatment B. And this is sort of a very upsetting thing. So you sort of, one conclusion tells you that first conclusion tells you that treatment B is better But then for every subpopulation, and these things gather together to make the whole population, treatment A is better. This is very upsetting to people. And this kind of paradox can be created essentially if I give you the more refined data, you can reconstruct a red dot like this. This is the actual data from the study, but just as a principle, if you have the more refined data on subpopulations, you can put that red dot anywhere in the rectangle that spans between those two dots. So you can really get a wide range of sort of full sample behavior from what you have in the subpopulations. So after this, you might think, okay, well, what the physician should do is, have them come in, and then before deciding on the treatment, scan, try and see how big the kidney stones are, and then decide what treatment to give, except it should always be treatment A. So why bother scanning? So what's wrong with that kind of conclusion that you should now switch to treatment A? I'm assuming many people actually know Simpson's paradox. And yeah, please.
So there should be some type of average. So some population has to be on the other side of.
Maybe with a microphone.
If it is averaged and all together go on one side of the linear function, and the two samples which one has sorted out on the other side, then if you make enough fine-grained scale, there should some go also onto the other side of this linear function.
If I break down to some smaller subpopulations,
Smaller populations, some subpopulation would need the other treatment.
So I think, yeah. So I actually think not. So let me show a picture. It's an interesting idea, but I think it's not true. Let me show you the next piece of data, and we'll see. I think that's not true actually. But we should think about this more. So, okay, so up till this, everything I've shown you is actual data from the paper, and it seems to suggest that, on further thought, maybe you should give treatment A. I left out, oh my God, I left out, in the interest of time, I left out the next picture. Let me tell you what the next picture is. You can do something synthetic with this data. It's not actual medical data. You can further refine the blue dots, those blue populations, and it's going to some other criterion. Let's say the patients who showed up in the morning for treatment and those who showed up in the afternoon for treatment. You could do like an invented thing like this. And you can create now 4 subpopulations, and you can push those 4 subpopulations all above the 45-degree line. So you could, upon further refinement, come to the conclusion that, everybody should get treatment B. Or you could like mix and match, you could like create anything you want. So in particular, I don't think it's true that even if you line up all of them, even if there are many, many populations, you line up all of them on one side of the line, I don't think you can force any of the aggregated populations to be on that side necessarily. Okay, so what's missing in this picture is there's no model for how this data is being generated. Okay, so the thing is that there's this latent variable, which in this case was stone size. So in this case, this is a case where we actually figured out what this latent variable is. And what it did was it simultaneously influenced the treatment and the outcome. What was going on in this data set is that there's a strong positive correlation, and you can see that in the sample populations if you looked. There's a strong positive correlation between the stone size being small and the treatment, the physician giving treatment B. Essentially, so then now the graph looks like this. There's a stone size, and it affects 2 things. Which treatment the physician gives. Even if the physician doesn't know the stone size, it affects the symptoms. How severe are the patient's symptoms? So it doesn't have to be because the physician knows the hidden variable. He doesn't have to have done any scan. She doesn't have to have done any scan. It's just the patient didn't look quite as bad, so treatment B will do. And that also affects the treatment outcome. The patient wasn't as sick, so they do better. If you can figure out what that hidden variable is, and you condition on it, you can calculate the causal effect. So this is becomes these become the statistics now of 2 noisy channels that refine the picture. There's something that happens in the presence of small stones, something that happens in the presence of large stones. Okay, so this is Simpson's paradox. So okay. There are a lot of examples of this paradox playing a role and sometimes getting a lot of publicity for it. There's an old case of a lawsuit at UC Berkeley on female versus male graduate admissions. Recent one that I read about, I don't know the details about, was in comparing COVID infections in China and Italy, the over fatality rate being higher in Italy, but in every age group, the fatality rate being higher in China. I don't know the details on that study, but sort of counted this. Okay, sorry, this is the plot with the made up data. So these 4 green points all being above I forgot the order of my slides. Okay. So that's my first paradox I was going to tell you about. So we need there's this paradox, and it kind of gets resolved once you understand the proper model of how the data is being generated. Second story. Second story has to do with mainly with 2 figures known as Raymond Pearl and Joseph Berkson in early half of the 20th century. This was still kind of the early days of modern medicine, if you will, and physicians had this idea that there were diseases that could be antagonistic to each other, or maybe in our language, that one would repress the other. And in 1928, Raymond Pearl, working at Johns Hopkins, went out and studied 1,632 cadavers. And he looked at these cadavers and looked at whether they had cancerous tumors. And or we split them into 2 sets of size 816 each, half the population, those that had cancerous tumors in the body and those that did not. And then he also looked at their lungs and whether they had the symptom of tuberculosis, tubercular lesions. And he found that the cadavers that had that were cancerous tended to not have had tuberculosis. Okay, so he sort of hypothesized this kind of antagonism, saying that tuberculosis might repress getting cancer. And then he followed up with the natural conclusion from that, which is what? Well, if you think that tuberculosis might repress cancer, you should. Okay, it's not good. You might view using something from tuberculosis as a treatment against cancer. Not actually giving people the disease or not actually giving disease, but what he did is two things he did. He exposed a population of rats to a protein extract that you get out of tubercular lesions, and then he observed the rates of cancer in those rats. And in people, he didn't do this, but he took people who had very advanced malignant cancer and studied them for their last few months, and to try and see whether this treatment with tuberculin helped them at all. And these cancer treatments, so to speak, didn't work out very well. We don't treat cancer this way then, and they didn't even treat cancer this way after that. But he soon thought better of this, and he said, there's maybe a different explanation for this negative correlation, if you will, which is it might be alleged that the reasons why people with cancer are clinically found to have less tuberculosis, as it were, is because the cancer kills them before it's time for the tuberculosis to develop. It's kind of, I don't know, we can come from it from our perspective, and we've all been primed to look for these things. Then maybe it's not so shocking. But it got formulated, it was at the time, and it got formulated a little bit later by Joseph Berkson, another physician. And he kind of explained this and wrote it up in print in 1946. And so it gets called Berkson's fallacy or things like this. And there have been a lot of follow-ups on that. And what's happening in our language, in our graphical language, which is a good way of understanding these things, is that there's a selection bias. When we look at cadavers, we are literally selecting for the person being dead. And either tuberculosis or cancer can be causes of that. So there's this measurement of, is the person you're looking at alive or dead? And it creates it can create some kind of selection bias. And in particular, if you it's what statisticians call this missing not at random problem. You could think of it as a missing data problem, that when you're studying cadavers, you're missing the living. Okay, So literally, the disease statistics in the population might be like this. T equals 0 means no tuberculosis, T equals 1 means yes, C equals 0, C equals 1 for cancer. So your kind of relative populations might be some A, B, C, D, but in the dead, if there are only sort of 2 fatal diseases, you don't see anybody who doesn't have one of these problems. So your statistics change by, and this is the missing data. And in the presence of this kind of a missing data, you can prove easily, as an exercise, prove some lemmas that show that the covariance goes down, or that the correlation coefficient goes down in the dead. So the 2 things could be independent, but you would get negative correlation after the selection bias when you look at cadavers. So these are my 2 paradoxes. These confounding variables, the presence of confounding variables, needing to deal with that, and the presence of colliders are both things that that affect our, I don't know, this is plugged in. Yeah. Check the other end of it. I don't know. This one. You think that might help? Okay, let's see. So these things both cause distortion in our statistics, and we can't really resolve. And they create situations that we cannot resolve just from the data. And these are the two paradoxes or fouls, that we've just observed. And the wonderful thing, and that's why I call it this sort of tale of 2 paradoxes, is that these are really the only problems. So this was sort of worked out by Verma and Judea Pearl, unrelated, I believe, to the other Pearl, in 1988, so quite a while ago. And I'm going to spend now. Okay, those are my tale of 2 paradoxes, and now I'll show a little bit more rigor about the model that we're looking at, the models that we're looking at. So I'll define a causal network to be a digraph that has 3 kinds of vertices, really. And has these edges, and they're all directed edges. The observable variables are X union Z, and these are disjoint sets. And then there are these latent variables, U. And I'll always shade the latent variables, and I'll always sort of double box the observable. So I'm not necessarily marking any of the Z set. So I'm not necessarily putting any Z's here. So a model might look like this. This would be like a hidden Markov model. You'd sort of have this Markov chain on things that you don't see, and then you get to see some little bit of data about each one of them. That's a classic kind of model of this type. This is something called the front door model that's important in causal inference. This would be a mixture of product distributions. There's some latent that you don't see, and then there are these populations, but conditional on in each population, which is fixed by the hidden variable, you have a conditionally independent random variables. These are 3 little examples of the types of graph that we'll see. And script P, or calligraphic P for the remainder of this talk, is our data that we get. It's this probability distribution, the joint distribution on all the observable vertices, X union Z, not including, you don't get to see the latents. Okay, you never get to see the latents. And this model, what does the graph have to do with the probability model, is that it has to be a Markovian. So this is a crucial equation for understanding the rest of the talk. If you don't know directed graphical models, is that the probability of any particular assignment x1 through x sub n is going to be the product over vertices of some conditional probability given the parents. So you only have to look at the parents of a vertex to decide this probability. Okay. This collection of conditional distributions, these are the parameters. These are really a list of essentially noisy channels. Each term in this kind of a product is what's the behavior of this noisy channel. Okay, so except it's a noisy channel that might take in the input from several vertices, and it gives you the value at x sub I. Okay, so that's the kind of the core information. These are the parameters of the model you might be interested in. And Z kind of play a special role. These are the conditioning or selecting vertices. These are the ones that will sort of double boxes that can affect, you can do selection bias. So now I have to give you one nice definition. If you walk away and remember this definition from today, you'll maybe learn something about causal inference. It's a very nice notion, if you haven't seen it, of vertices being deconnected. This is the term that's used. So X and Y are deconnected, given a conditioning set Z, which I'll write in this form, X sort of tilde Z to Y. If, and I'll give 5 examples here, if one of the following thing happens. Either well, let me start from the figures. So the easy figures are this, that, if X has a path to Y or Y has a path to X, then they're deconnected in the sense that, it's sort of to suggest that they're connected, there's sort of, in this case, there's a clear causal chain from X to Y or from Y to X. That's the simplest kind. The more complicated kind, and that's included in this as a special case, includes this as a special case, is that there's some vertex A naught up here at the apex, let's say, and then there are directed paths from A naught to X and from A naught to Y. Okay, where not going through any Z vertex. Okay, so this is another way that X and Y can be deconnected, is that there's some kind of source and there are paths from that source to both of them. And then what makes this definition kind of, and you don't go through any Z vertices. And then the thing that makes it kind of more interesting is another way to be T-connected is that there is some Z vertex such that X is deconnected to that Z vertex, like here, like I'm showing with the laser pointer, and Z is deconnected to Y. Okay, but, and this is shown in the last example, you can also iterate this through Z vertices. You can go through many Z vertices in this way. So you can have many of these sort of arcs, if you will. You can go, and you can kind of bounce off of these Z vertices. Okay, so this is called two vertices being deconnected. It's a very interesting definition because it gives you the following theorem, which is sort of fundamental to the area. So if you just want you kind of take it away. So two sets S and T are deconnected conditional, with this conditioning set Z, if there exist X and S and Y and T that are deconnected. And otherwise, we'll call these two sets that they're D-separated. And here's the theorem that makes why this deconnected graphical definition, what's interesting about what connects it to these probability models is this very nice theorem that says that S, the set S, is deconnected to T if and only if for almost all, so there's some boundary or something with it, but for almost all probability distributions that are Markovian on the graph, and every assignment to these measurement variables, the Z's, the random variables associated with it, S and T, are dependent in the distribution P conditioned on that assignment to the Z's. Okay, another way of thinking about that is that if S and T are not deconnected, then you get independence in the distribution between what's happening at S and what's happening at T. Okay, so it's a very powerful fact that this is an exact characterization. So, and this is why, although I won't necessarily make, it won't fill in a lot of the blanks on connecting things up. This is why in this talk and throughout this kind of literature, we can just basically focus on this graphical theory, although you don't have to. There are some other ways to do things. Well, Z is kind of one of the arguments there to the that would probably be a more concise notation, but this is what's, people will say deconnected with this, conditioned on Z. That's the usual way people say it. I agree. It would be, maybe dependent. I don't know. Does anybody, I don't remember. Well, somebody's, yeah. Not sure. Okay. Maybe directed, I'm not sure. Okay. Okay, so here's our goal. What do we want to do with this theory? So, so the main goal I'm going to talk about, and there are others, but what I'm going to talk about is the ability to answer these kind of statistical what-if questions. The kind of things that I could have answered with a controlled experiment if I could have done those. So what would be the effect on patient outcomes if I choose this treatment or that treatment? What will be the effect on education and employment if I legalize marijuana consumption? What will be the effect on employment and interest rates if the Fed does such and such? They would love to know that. What will be the effect on world grain production, a few maybe decades down the line, if CO2 concentrations rise to such and such? That you might care about the answer to that. Many such things. So now every one of these, and I'll allow, every one of these is sort of a thought experiment of the following type. You say, well, the world behaves a certain way, and I can make a freely chosen intervention in the world. I get to contemplate, changing the world in some way, and then I want to know what would happen if I did that, which is there's something very arrogant about that. If you get a little philosophical about it, it's like, really? I mean, and people have had a lot of trouble with this. So since this is one of these kind of hour talk, plenary talks, so their speakers get a lot of it. Maybe they even sometimes get brownie points for becoming less technical and just I don't know, I'm not sure. So bear with me. I'll try, and you'll tell me later whether I should have done this diversion. But I really bothered by the question of free will. Don't know if you've been disturbed by that yourselves. But this is really about free will. This is really about supposing that I'm not part of the system, that I have free will to kind of go and do something. And when I started getting interested in these things, I say, like, really, how do they justify their model? No one talks about too much in the, I mean, I write papers, and I don't talk about this, you probably career suicide to write about this in your papers, but so we assume that the system acts according to its own dynamics, but at the same time, we suppose that we have free will. And frankly, this is about every one of us goes about living our lives. And people have been bothered by it for a long time before there was a scientific method. I promise you, I didn't come up with this quote just because I was coming to India. I came up with this quote several years ago, but it's a wonderful quote. So I know everything that happened in the past and all that's happening in the present and all things that are yet to come. So this is a statement that the world somehow has a course that it's undergoing that's kind of not up to you. It's set. In the West, a little bit later, but from our point of view, similar time period, Lucretius wrote, if all movement is always interconnected, the new arising from the old and in the deterministic order. So in other words, if physics is deterministic, and so forth and so forth, then what is the source of the free will possessed by living things throughout the earth? So how are you so arrogant to think you have free will? In the Jewish sources, roughly the same period, there's a famous quote: "Everything is foreseen, but freedom to choose is granted." So this is our rabbis kind of like, well, it's all fixed, but you still get to choose. I don't know how but it's not that it resolves it. It's just sort of telling us that 2,000 years ago they were troubled by the same thing. There's a wonderful quote from Samuel Johnson: "All theory is against the freedom of the will, but all experience is for it." And this is how we live our life. And then finally, there's a quote from The Matrix. I'll let you rewatch the movie yourselves, and if you haven't seen it, it's a great scene. Maybe I won't read the whole thing. I'm just on time pressure. Okay, so so intervening. So now we've allowed ourselves. We got past that. We're allowed to intervene. What is intervening in the language of these graphical models? So it has a well-defined meaning. An intervention on some variable x. So let's suppose this is my graph. An intervention on a variable x is the following kind of thing. I take the graph and actually change the graph. I have an intervention variable x. I remove all incoming edges to it, which means x is no longer being statistically determined by its parents. It's being determined by me. And then I can get, so now in the observed probability distribution, it's meaningful to ask what's the probability of some assignment y given the value x. But that is not a causal datum, value. That's a correlation that you're observing, okay? This other thing that what we're describing here, probability of y do x, is take the modified graph and look at the conditional probability there, where I get to pick the value of x. Now that's of course causal, because there I'm actually choosing the value of X and I'm seeing what's the statistics at Y. So that's the causal thing that I might be interested in, you know. So and the tricky thing that kind of makes for this to be a very interesting area to look at is that, of course, in general, these things are not the same, because in my observed statistics, I'm seeing things with all the correlations that are not causal that happen in this case, in this diagram, because of some common latent, for example, whereas over here, I'm taking the latents out and I'm determining it. So, and one of the questions we want to know is when is it even possible to go from the knowledge of the joint distribution in the original graph to the interventional distribution, which is in some different graph, some modified kind of a graph. So there are two main areas, and I'm gonna very rapidly. Okay, so I've now done two of the things I set out to do for you. I've sort of told the story of these paradoxes and how they motivate these graphical models. I've told you what intervention means, what we'd like to study, and I'd like to now tell you, you know, in some completely biased survey-ish kind of method, you know, some of the results, some of the classic theorems, and some of the open questions, and it's very biased, and you'll have to. So roughly speaking, and it's not everything falls into these two umbrellas. Part of determining, there's a little bit too many INGs over there. One thing you might say is, I don't really know what the graph is. I have all these variables, you know, medical data on patients, or you know, sea levels or something, and I don't know what variable is kind of affecting what other variable. What are the dynamics? What's Markovian here? What's a Markovian model for this? So that's one kind of a problem. And the other kind of a problem is if I sort of know the Markovian model, but I want to know the parameters. That was what I was a little bit talking about on the previous slide. Like I'd like to know what the conditional, what the model is. And both of these are relatively easy if there are no latents and all, if everything's observable, with some technicalities I won't talk about. But they're interesting questions because of confounding and post-selection. So this is going to be a very a lot of selection bias, as I said, in what I talk about. So let me start with the first of those, and I'll tell you a few slides just on the first of those, which is like, what is the graph, the causal discovery? So here's the ideal answer. The ideal answer is don't try and do that from statistics at all. So this is a question which often, I don't know about often, but sometimes you can get access to without any statistics, just from knowing the kind of the physics in quotes of the system. So here's an example that should concern everybody here, because we all send papers to these conferences and get annoyed at the referees when they bounce back and so forth. So here's a model for why you do double-blind refereeing in conferences, or why you might want to. Not all conferences do. And the idea is this: we all know that there are fashions in the field. New things come in, they're good, they're not good, they're in fashion, they're out of fashion. So we know that those fashions influence both what papers get written and how the PC views those papers. Okay, and that's fair. That's that's just how the field evolves. You know, everybody's kind of participating and thinking about things, and that makes sense. But what you don't want is that the author identity should have a hand in this, right? So you kind of, on fairness or some kind of a principle, the argument is, the fact that it's some very famous person, we shouldn't necessarily follow their trend, or we shouldn't reject some interesting thing just because it was written by a solo grad student or something like that, right? So this is the argument for, and you can come up with arguments against, actually, but this is the argument for. It's a good argument, and that motivates that your graph, you want your graph to look like this, and you can get your graph to look like this if you anonymize author identities. So that's nice, but of course, often you don't get to design the rules for whatever is going on. And so there is a statistical way of approaching this, which is you say, given whatever the joint statistics are in my observables, I'd like to find a minimal graph with respect to inclusion, for which these statistics are Markovian, as given in the definition, kind of back toward the beginning. Okay, so this is one branch of research. There's a classic algorithm for this. Classic means it's about maybe 25 years old or so, or maybe a little, something on that scale. It's called the PC algorithm, and maybe I'll skip it. I sort of have only like a quarter of an hour, and I probably shouldn't overtake. So it's actually quite simple. So you sort of do these conditional independence tests, and gradually you start imagining that anything could be. You start by determining the skeleton of the graph. You start by imagining that it could have been the whole clique, everything connected to everything. And by some conditional independence tests, you can start finding reasons to remove edges. And so that lets you determine the skeleton of the graph. And then finally, at the end of that process, you can also determine these things that are called immoralities. So sometimes you find yourself with a skeleton that looks like this, where the induced subgraph on some 3 vertices is just a path, okay? Under those conditions, you can determine you can identify using these conditional independence tests, you can determine when it's the case that you get with a collider there. A collider is these 2 edges coming in, that configuration, right? There are 3 other ways that the arrows could be pointing. You can't distinguish among those, but you could distinguish those 3 from this one that I drew here. And at the end of this process, you have determined correctly the underlying graphical model up to an equivalence class known as the Markov equivalence class. Some of you will know that otherwise. And there's a lot of interesting questions about how big Markov equivalence classes are. There are a lot of unsolved kind of enumerative combinatorics type questions in this area, which I'm not going to list any of those, but this only works when all the variables are observable, which is kind of the boring case for causal inference. Because when all of the variables are observable, causal inference is no different from just looking at the conditional probabilities. So, of course, people were interested in taking this further, and you can take it further. And there's something known as the FCI algorithm and some more recent version. And even in the presence of hidden variables, it is possible to make some progress, but much less progress. It's not as crisp a situation as for the. And I think it's not something I'm very expert at. But okay. So here are some on this causal discovery. I said I'd try and mention some of the main results, some of the main questions. So the PC algorithm I just described, it depends on these conditional independence tests. So conditional independence means I take 2 variables, 2 vertices in the graph. I want to know if they're independent after I condition on the value of some other set of variables. So the problem is what to do in the case of continuous random variables. So something that as computer scientists maybe we think about a little bit less, but a lot of the literature in this thing has to do with real valued random variables, temperature, CO2 concentrations, pulse, you name it. So in that case, there's a big question, kind of what's a good way to actually measure conditional independence. And so that's a very active area of research. Which if you have leanings toward this kind of area, these are some of the references you might want to pick up on. As I said, we don't have a full characterization of what you can do in the presence of hidden variables. There's some recent work that I've been involved with where we generalize the PC algorithm to the case where there's a hidden variable that can affect everything in sight, which normally should make any conclusions kind of impossible, but that it's cardinality bounded. Okay, so this is a theme that I've been doing in some of my work, and you'll see more mentions of this. So when you take these latent variables and you say, well, things are impossible if it's completely general random variable, but if you say it's something that takes on only 2 or 3 values, it's raining, it's not raining, whatever, then some things become possible. So this is the recent work with my with Yuval Rabbani and Spencer and 2 students, Bijan Zahari and Spencer Gordon. So we can sort of modify these conditional independence tests into rank tests, and then there's a lot more work, but I won't talk about it more at all. So that's one branch, causal discovery. That was like, what's the graph? The other main umbrella area, which I've worked on, more, and maybe I'll say a little bit more about, actually, is the causal identification problem. So I actually know I suppose I actually know the graph, but I want to know the parameters of the hidden of the the local conditional probabilities. And I want to know specifically if I have some intervention variables X and some response variables Y, I want to know, can it be, this is a computation I do just from the graph. There's no probability, there's no statistics on the joint variables rate yet. So when I'm looking at the graph and I say, here are the variables I might be able to intervene upon. Here are the variables I would like to affect. Is it possible for me, from information just on the observable, from the joint statistics, should I collect them, to determine the causal effect? Sort of like saying, should I even do this study? Should I even go out and gather all these observations? At the end of that, what will I be able to conclude from it? Will I be able to conclude from that data whether smoking causes cancer? Well, we'll talk about that example. Maybe not unless you kind of can enrich your graph a little bit. So this is a question, as it happens, to which there's a very beautiful answer, very non-trivial and beautiful answer, by Tian and Pearl, and then Huang and Valterta and Spitzer and Pearl, a few papers that developed this, that you can always answer this question. There's a polytime algorithm that takes the graph, including information about where hidden variables are, and says, okay, if you were to get the joint statistics on the observables, could you or could you not compute the interventional distributions? So you inputs G and the subsets X and Y that you're interested in, and you either get a map from the joint statistics, happens to be a rational function, to this probability of Y do X, the intervention, or it proves to you that this is impossible. It's a wonderful theorem. And there are public implementations of it. They're buggy, but my student wrote one that works. So I don't know. There's probably multiple public implementations, but the main one that's in R, I'm not recommending to. I forgot to mention, for the previous thing, for causal discovery, there is a widely available and very good as far as implementation. Let's talk about this example of smoking and cancer. It'll give us the classic example of something where something cannot be determined. Okay, I'll just spend a few minutes on this because it's I think motivationally, historically, it's kind of a very important example. And it'll let me show you at least a theoretical example of where a better graph lets you do things. So this is actually the history of how smoking, how smoke. I mean, this is a small excerpt from the history of the story of smoking and lung cancer. So you probably all heard of Ronald Fisher. Maybe the most preeminent statistician of the first half of the of the 20th century, and the smoker. And so in the 1920s already, it was sort of observed that there was this positive correlation between smoking and cancer. And I mean, 1928, I think some paper came out sort of documenting the correlation. And gradually, people got made kind of more and more noise about this, until actually already in the 1950s, the Surgeon General in the United States, started a long series of announcements first saying that smoking and cancer were correlated, and later even saying, some of the later announcements even saying that smoking causes cancer. It's an interesting thing. I think very well justified, but not scientifically justified, because they didn't have any causal model in which to determine that. They were just going on. Yeah, this is why this is an interesting area. But I should say that, Ronald Fisher, his smoking habit may have probably, I'm guessing, affected how he came out on this issue, but his arguments against were quite sound. And his argument, which is in this paragraph, this is his paper in Nature in 1958, or a small article in Nature in 1958, was this. He said the suggestion, among others, that might be made on the present evidence without any direct causation being involved, so this is his suggestion, that both characteristics might be largely influenced by a common cause, in this case, the individual genotype. So people knew about, Mendelian genetics and everything back then. They didn't have, you don't need amino acids to know anything about Mendelian genetics, right? So he says, we have genetics. I don't know how they work, but we have genetics. And he says there's some genotype that, and he didn't draw this graph, but he's describing this graph. He says there's some genetic factor that causes you to smoke it, and also causes you to get lung cancer. You crave nicotine, and some why shouldn't these things? There's a lot of correlations in behavior. Why not? And he writes with some annoyance that oh, someone dismissed my argument, but he says no one doubts the importance of the genotype to getting cancer of all types. So he wrote this article, and Harry Green was the chairman of the Yale pathology department, and he wrote sort of a similar thing, more or less. You know, you'll have to pry my pipe from my cold dead hands. That's a nice quote, but it's along those lines. And Joseph Berkson, the same figure we met before, also wrote similar things. Okay, so then the problem was that you had just had this little graph in which causal inference is actually not possible. Now, what if you would have this graph? This is a theoretical graph. This is not based on some study, but this is an example that Judea Pearl gives. Suppose there are these genetic factors and they do cause, suppose that were the case. Could you still figure out, okay, maybe there is a confounding variable. We don't have to say that there isn't. We just want to know, can we figure out the causal effect? There still could be a causal effect, even though there's some confounder. And there's a wonderful phenomenon, which is that if the graph were to be this, if you could argue that the only way smoking causes cancer is through putting tar deposits in the lungs. Smoking certainly creates tar deposits in the lungs, that's clear. And tar deposits in the lungs, that's this big deposit. If you've ever seen these like scans, I mean, it's horrible. So, you know, it's not a big leap to jump that would, to suppose that would cause disease. So all you have to say is that, you know, when people get tar deposits in the lungs, they don't get it from genetic factors. There's no genetic factor that causes tar deposits in the lungs. Okay, you have to get it from something, like smoking. You have to do physically something to bring that tar in. The body doesn't create its own tar. So it's not far-fetched to imagine that you could create this graph and then you'd look at every patient and see whether or not they have tar deposits. And the wonderful thing is that actually if you have this extra data, then you can determine the causal effect of smoking upon cancer. It's kind of a wonderful example that just one more item of data carefully chosen to get the right kind of a graph where causal inference is possible changes the situation entirely. And it's so easy that it's not trivial, but it's easy enough that the formula for doing the causal inference is actually on the slide. I'll skip it.
Getting targets.
Well, yeah, then this would be defeated. Then this would be defeated. It's crucial that there is not an edge there. Other question? Okay, so now I'm going to talk about, so that's like a classic theorem. It's my favorite maybe theorem in this area. So I'm going to talk about a few things that have been done and a few open questions and try not to go. So one is that something that Piyush and I did in 2016. We were interested in the stability of this inference. So it's fine to say, you know, the problem is that when you do condition, if everything's observable, not only you get the conditional probabilities directly, and they are also the same as the intervention probabilities. And so it's always very stable with respect to your data. The function you're trying to compute is basically the input. So you're not quite, there's some concatenation, but it's a very stable statistically question. And we were interested in, since this algorithm that I just mentioned on the previous slide, there's a kind of a whole recursion, and you might worry, is this statistically stable, this possible, this process? And so we found some bad news and some good news. The bad news is we actually found that, yeah, in the worst case, there are some Markovian graphs where this algorithm applies and tells you I can do the causal inference, but it's quite unstable in the statistics. So this complicated, it's not the algorithm statement is not so complicated, but the kind of recursion as you unfold it can create this instability. So that's one thing that's a little bit bad news. And it's a property. It's not that the algorithm is bad. It's the problem. The problem formulation has some numerical instability. On the other hand, we also found that if your graph is not kind of worst case, so if your graph actually is kind of a good case, then the algorithm is quite stable. So depending on what graph you get, you could look at it and maybe you could even do. We only kind of give these extremes, but we can characterize this good cases, and we don't have a general algorithm for saying what's the instability of any particular algorithm. That's itself any particular graph. That in itself is an interesting question. So, and then more recently, we came up with another different class of well-conditioned examples. So there's hope for these things. The numerical instability doesn't have to kill necessarily the example that you're interested in. Here's another question that has to do with the causal ID problem. As we've seen, so here's the thing is that there's this theorem that I said is my favorite theorem. It tells you either here's the intervention effect, or it's impossible. And the problem is that, like in most cases, it says impossible. Regrettably, when the graph, it's sort of the denser the graph is, the more hidden variables there are, and in sort of generically, you'll get the answer is nope. There's no, you can't do this. So, what do you do under those situations? So one thing that I've been doing in my work with students and colleagues over the last few years is saying, okay, what can we do when we posit that the hidden variables take on few, they're categorical data, they take on only few values. I've already mentioned this before. And in that case, it becomes, there's like all kinds of wonderful things you can do. And you can get quite good answers, because the kind of confounding effects that you get when from a hidden variable, the way that a hidden variable can destroy any notion of causal inference is if this hidden variable can affect everything in the graph, you can just toss the random bits kind of locally and then tell everybody else what value to take on, and there may not be any causal effect between anything, and you can get the data to look like anything. But that requires that this hidden variable have a lot of state to be able to take on like 2 to the n states if there are n binary vertices. So if you cut down the state space of this hidden variable, that counter argument kind of goes away, and then it turns out that in fact positively there's a lot you can do. Another work, and I want to end more. Okay, I'm already slightly past time, so I'm going to abbreviate. Another thing you can ask is what's the complexity of this kind of a problem when you have many hidden variables, but they're independent of each other. Also, a lot of fun things can be done. If you've heard about restricted Boltzmann machines, comes up a lot in neural nets, then there's a very strong connection between this question and what happens in restricted Boltzmann machines. Restricted Boltzmann machines are undirected graphical models that look like complete bipartite graphs. We're in a directed model, but they're actually very closely related. I won't have time to talk about that. Another thing I've been doing recently with Michael Langberg is saying, well, if X and Y, in this particular graph, you can see that X and Y are deconnected. Remember the definition of deconnected? The deconnected, ignore the direct effect there. The direct effect there is what we're interested in. That's the effect of X on Y. Suppose we want to know what that causal effect is. And if that were the only edge in the graph, that would be great. We could just, it's just like having a controlled experiment. Unfortunately, there's also this deconnected path, this zigzaggy one that goes through a lot of colliders. And that destroys the possibility of doing this logic. But if it's a long path through a lot of colliders and there's kind of noise on all these processes, you would think that you should get a kind of exponential decay and maybe be able to eventually say, okay, just ignore that term and it doesn't affect anything significantly. So that's recent work with Michael Langberg. There are other questions about determining the channel region. When the answers are not, when the ID algorithm outputs, nope, this is not identifiable causal effect, you can turn around and say, okay, fine, you can't give me, it's a point, it's an actual model, but can you give me a small range of models that, up to, so there's work on that and going back quite a long way. There's a lot of work, this is my last slide, so I'll tie up here. There's a lot of experiments on relaxing the notion that you're doing everything only passively. So everything I've talked about today is supposing that you, the scientist, are working only with passively gathered data. You have no possibility of experiment at all. There's been a lot of work on saying, suppose it's more that like experiments are very expensive and I have to kind of do mostly observational and they're pay for doing a few experimental interventions. So then you need to study like, how many such interventions do you need? Where should you intervene? All these kind of questions. And there's been a lot of work in the last 2 decades, sort of on that. There's more work. Maybe one thing to mention here is a nice paper on when you're getting selection bias because of human subjects. declining to participate in your survey, which is like a big issue, because that's exactly the kind of behavior that creates selection bias. People with risky drug behaviors, not telling you the truth about, or refusing to tell you anything about their habits, things like that. So then the question is how to incentivize cooperation so that you can get more stable. So there's some work that ties into the whole algorithmic mechanism design field. So okay, so I'm slightly over time. I'll stop and.
Uh, hi, Leonard. Here, to your left. Here. So, what would a certificate for impossibility look like? I mean, like the algorithm that you mentioned, where
Yeah.
it either produces the intervention distributions or says that this is impossible. What does a certificate look like there?
It's a graphical substructure called a hedge that looks roughly, I don't have a word, looks roughly like this. You take the response variable y that you're interested in, and you find a directed tree that's leading toward the response variable. So sort of a an edge going into y or into some ancestor of y, and then sort of a tree. You find this kind of a tree, and then another tree that contains it as a subset, and some more details. And with the presence of this thing that's called a hedge, sort of, I don't know, one tree towering over the other or something. Anyway, this hedge, so it's some graphical substructure that's the proof that, and the point x, the intervention variable, has to lie in the bigger tree, but not in the smaller tree. That's a key point. So if you have that kind of a graphical substructure, then the causal effect on x upon y cannot be determined. That's the.
So is it like, I mean, from that substructure, is it possible to construct two different causal graphs
It's
that have
not two different causal graph. It's possible to construct the two different causal effects. So upon, because the whole graph, but it's possible because there are some hidden variables. This thing doesn't happen if there aren't hidden variables. I'm leaving out some details. So these two trees also have to have a certain property with respect to how the hidden variables are behaving. So what you can create is two probability models for the same graph, the same hidden variables, two different probability models for them in which the hidden variables are doing something different, and the computations at the vertices are doing something different in the two models, in such a way that the effect of x, the causal effect of x upon y, is different in the two, but the joint distribution that you on the observables is identical. I don't know if everybody else can hear you. That would be maybe more the question.
Oh, thanks. I think that's quite interesting. I guess I'm so what you mentioned with like the ID problem, that instability you were talking about coming from the problem itself. Is it worth asking, or do we have any sort of notion of like different structures of like these causality graphs and how that affects this instability arising, and sort of how we can design questions, experiments to try and mitigate that?
Yeah. So there's a decent understanding of that. There are these things, I had to go by it for time, and the things, but these things called districts or C components. And generally speaking, everything about causal inference which, if there are no hidden variables, all the C components are just individual vertices. And in general, the C components kind of aggregate together vertices among which the hidden variables have some kind of confounding effect. So roughly speaking, the actual test is you imagine, okay, if I could get this graph, and you can just crank it through the algorithm and say, would I have my causal effect? Roughly speaking, the smaller you can make the C components, the better shape you're in. That's the crude answer. Don't know if I answered your question.
Cool. Thanks.
Sorry, forgot to get your sign on this. I guess they, now it's, this is maybe the.
So,
No, sorry.
oh yeah, turn this off.
Right. Yeah. All right. It's uploaded, taken care of. But I already have the signatures. Hello, like my part is done. Just check. Yeah, this is on. Yeah. So, shall we? Yeah. Is anybody going out and clap? Yeah, so Shrikant went out. So the tracky chair himself is going to go out and clap. So, yeah, but we can actually start. All right. Good morning, everyone, and welcome to the fourth session. In this session, we'll have two talks. The first one is about decision tree complexity versus block sensitivity and degree. The speaker is Swagato Sanya. Thanks, Karthik. I hope I'm audible at the back. So this is joint work with Rahul Chugh and Shupartho Poddar. Shupartho is not yet in the audience. Hope we'll get here soon. Never mind the date here. So let me start by explaining to you the terms on this title. So Boolean functions are basic objects of our study. A Boolean function maps each bit string of a certain length to a 0 or a 1 and are specified by a truth table that outputs its, that just lists its outputs for all input strings. You may have come across tables which are partially filled with many of the entries unspecified, and those are referred to as partial Boolean functions. However, here all our tables are completely specified, completely filled. All the entries are valid bits. So we focus only on total Boolean functions in this talk. All right. All right. So let me explain to you what decision trees are. That's the first technical term on the title. Through an example, let f be the three-variable function given by this logic expression. Decision tree that computes f is a binary tree rooted such that each internal node is labeled by a variable and has exactly 2 children, and each leaf is labeled by a bit. And given any input x to f, so x will stand for a generic input to f. X is going to be a vector x1 through xn, where each xi is a bit, right, throughout the talk. So given such a tree, you can run it on any input x as follows. You start from the root and look up the variable that labels the root and query it. So you will assume that there is an oracle who answers your queries. So, and depending on the answer you receive, you will query one of x2 and x3. If the oracle says that x1 is 0, the function simplifies to x2, and so you will query x2. On the other hand, if the oracle says that x1 is 1, you will query x3. And after your second query, the response of the oracle determines the value of the function, and you will navigate to one of these 4 leaves and output the label of that leaf. And you can verify that, on every input x, the value that this algorithm outputs is equal to the value of the function. So we will say that this decision tree computes this function. The complexity of this tree is its depth, or equivalently the number of queries that it makes in the worst case. And capital DF is a notation for the decision tree complexity of f, or query complexity of f. A decision tree is also called a query algorithm, and that is defined to be the depth of a shallowest decision tree that computes f, or equivalently the number of queries made by the best algorithm in the worst case. All right. So this is the next term on the title, block sensitivity. Let me explain through this example. Tribes is the function, Boolean function computed by a depth 2 and/or read once formula, where the input variables are partitioned into square root n equal sized blocks with square root n variables each. They are b1 through b square root n, and each bi is fed as an input to a distinct OR gate, and the outputs of the OR gates feed into the output AND gate, and the output of the AND gate is defined to be the value of the function on this input. Now consider the all ones input written down here, and this Boolean formula evaluates to 1 on this input. Yeah. Now consider flipping all the bits in B1, yeah, while leaving everything else unchanged. What effect does it have? So this OR gate switches to 0, and it in turn sets this AND to 0. So the function value flips from 1 to 0. So we will say that B1, the block B1 is sensitive for the input all ones. Similarly, each BI is sensitive. You can, like, if you flip any BI while leaving other BIs unchanged, the function value flips. So there are square root n sensitive blocks, and we take note of the fact that they are all disjoint. So on this input, there are square root n disjoint blocks, all of which are sensitive with respect to this input. The block sensitivity of a function for an input x, denoted by bs f comma x, is the maximum number of blocks that you can pack, all of which are disjoint for x. Block sensitivity of tribes for all ones is square root n. We just saw that it's possible to pack square root n blocks, which are all disjoint for 1 to the n. And you will be able to convince yourself that there is no way of packing more than square root n blocks, sensitive blocks. Block sensitivity of f, denoted by bs of f, is the maximum block sensitivity of f for any input x. And block sensitivity of tribes turns out to be equal to square root n. Yeah. Degree, the final term on the title. So here is a fact. Every Boolean function f can be uniquely expressed as a multilinear polynomial with real valued coefficient. For instance, consider the two variable AND function that's represented by the monomial x1, x2. Each xi is a 0 or a 1. So x1, x2 is 1 if and only if both x1 and x2 are 1. And OR x1, x2 is, by De Morgan's law, the complement of, that is 1 minus AND of x1 complement, which is 1 minus x1, and x2 complement, and which is this polynomial. Yeah. And this is not a special property of two input AND and OR. Any Boolean function on any number of variables can be represented by such a polynomial. Furthermore, in exactly one way, and the degree of a Boolean function is defined to be the degree of this unique polynomial that represents it. All right. BS and degree both are lower bounds on capital D, the query complexity, and I'll tell you why. These two are going to be the only proofs in this presentation, and these are not our work. So let's begin by telling you why BS is a lower bound on capital D. Consider any decision tree capital T that computes f, any input x, and any block B that is sensitive for x. The claim is that if T is run on x, it must query at least one bit of B, because otherwise you will flip B and capital T will not realize and will produce the same output. On the other hand, the value of f will flip, and that will contradict the assumption that T computes f. Thus, if an input has BS many disjoint sensitive blocks, capital T must touch each one of them and hence must make at least BS queries. All right. So why is capital D at least degree? Let me tell you that. This is because given an optimal decision tree that computes f, I can write down a polynomial with degree at most capital D that computes f as follows. Let's say this tree is an optimal decision tree that computes f, and I have shown one leaf L and I've shown the unique path of from the root of the tree to L. Now, what are the inputs X that lead the computation of this tree to L? Those are exactly the inputs in which X5 is 1, and X3 is 0, and X7 is 0, and X1 is 1. Yeah. So this polynomial GL can be easily seen to evaluate to 1 on these inputs that take the computation to L, and evaluate to 0 on every other input. The degree of GL is the depth of L. Yeah. And we note that fx is 1 if and only if x leads the computation of this tree to some leaf whose label is 1. And so f is equal, like f is represented by the polynomial obtained by summing up these GLs over all L whose label is 1. The degree of this polynomial on the right hand side of this equality is at most the maximum degree of any GL, which is the maximum depth of any L, which is by definition the depth of this tree, which is capital D. All right. So this is what we just saw. Degree and BS are both lower bounds on D. But how much larger can D be than degree and BS? It's long known that D cannot be too much larger. D can at most be cubically larger than BS and degree. And we want to know how sharp is these upper bounds, or in other words, is 3 really the exponents in the optimal polynomial upper bounds on D in terms of BS and degree? Yeah. Can D indeed, are there situations where D indeed is as large as BS cube or as large as degree cube? What is known is that there are situations where D can be as large as degree square or as large as BS square from earlier works. Yeah. So the optimal exponents for these two polynomial upper bounds lie somewhere between 2 and 3. And we are interested in this work in knowing what they are. Yeah. So in this work, we improve the cubic upper bounds for classes of Boolean functions. So ideally, upper bounds are to be improved for all functions. We cannot do that. So we considered 3 classes, and these are 2 of them. Graph properties is an important and central and well-studied class of Boolean functions. Functions with constant alternations may be slightly less well known, but it contains as its subclass the class of monotone functions, which is again a central and important and well-studied class of Boolean functions in Boolean. I won't be defining these classes, but the summary is that for both of these classes, both of the cubic upper bounds can be improved to quadratic. One of these results is the work of follows from a work by Turan, and the others are our contributions in this work. The third class of functions that we consider here are zebra functions. This is a class that we define in this work, and I'm going to tell you about this in the next slide. All right, so the picture on the left is of the Boolean hypercube, that is the set of all binary strings of length n, the domain of our function f, and where the strings x are arranged as per their Hamming weight, that is the number of ones in them from bottom to top, all zeros at the bottom, all ones at the top, and others arranged in Hamming levels. All right, so f is a, okay, before that, you can imagine, walking up this diagram from all zeros to all ones in steps, where in each step you flip a 0 to a 1, and there may be many paths that you can take depending on the order in which you flip the zeros. Now, f is a zebra function if on each of these paths the value of the function switches equal number of times. All right. So pictorially, a zebra function induces a stripe structure onto the Boolean hypercube. It partitions the Boolean hypercube into stripes. The value of the function is constant on each stripe, and is different on adjacent stripes. So here, for instance, the function is 0 on the white stripes and 1 on the shaded stripes. Zebra function is a common generalization of monotone and symmetric Boolean functions. A function is monotone if it has 2 stripes, switches once and then remains there. And a function is symmetric if it depends only on the number of ones in the x and not on the locations of those ones. And so it is a zebra function where the stripes are like horizontal bands and correspond to ranges of Hamming levels. So what do we prove about zebra functions? So let's consider symmetric functions first, which is a subclass of zebra functions. It's long known that for non-constant symmetric functions, d, bs, degree are all linear, and so they're linearly related amongst themselves. So the cubic upper bound reduces to linear upper bound. For general zebra functions, we show that capital D is at most bs square, that is the cubic upper bound on bs cube, the cubic upper bound of bs cube improves to quadratic for these functions, and it's tight as witnessed by the tripes function that I showed you earlier. That's a monotone function and hence a zebra function. Okay, our second result falls short of showing that D is at most degree square. What we managed to show is that certificate complexity, which is a smaller measure than capital D and denoted by C of F, is at most degree square. However, the best upper bound on certificate complexity in terms of degree known for all functions is cubic, and this is an improvement of that upper bound. Sorry. We leave the question of whether or not capital D is at most degree square for zebra functions as an open problem in this work. All right. So next, I want to tell you about a connection between our question, what I have been talking about for so long, that is the question of upper bounding capital D in terms of BS and D, to the two-party communication model by you, to communication complexity in general. So we considered the two-party communication model by Yao. Yeah, F and X are as before, and consider a bipartition of the bits of X into 2 parts, and the parts are, let's say, X superscript 1 and X superscript 2. Yeah. So as an example, let's say X is X1 through X5, X superscript 1 is X1 and X3, X superscript 2 is the remaining bits of X. And you give the 2 parts to the 2 parties. So there are 2 parties, Alice and Bob. Yeah. Alice gets 1 part, Bob gets the other part. And they jointly want to figure out the value of fx, but none of them has access to all the bits in X. So they exchange bits. They can do local communication, and there is no restriction of how much communication they can do. What I'm interested in is the least number of bits that they need to exchange to figure out the value of fx. And that number is defined to be the communication complexity of the function f. To specify a communication task, the bipartition also needs to be specified. However, that dependency is suppressed in this notation. All right. I want to compare C and D, CC and D. Yeah. So suppose you give Alice and Bob a decision tree that computes F. Yeah. Then it's straightforward to verify. For now, you can trust me that the 2 players can simulate the decision tree with no overhead. They can simulate each query by exchanging 1 bit. Yeah. Thus, they can just simulate the tree and compute the value of f by exchanging at most as many bits as the depth of the tree. And this immediately implies that CC is at most D. So we are interested in proving upper bounds on capital D. Now I want to consider proving upper bounds upper bounds on CC instead. And in light of what we just saw, this is a potentially easier task. So our next result shows that upper bounds on CC translates to upper bounds on D. So it's sufficient to solve this easier problem of upper bounding CC. So we reduce the task of upper bounding capital D to the potentially easier task of upper bounding CC. So formally, this is our first result. So there are polylog n factors sticking around that I'll brush under the rug. It says that if for every f and for every bipartition of its input bits, CC is at most degree square, then for every f and for every bipartition of the input bits, capital D is also at most degree square. The next result says that if for every f and for every bipartition of the inputs, CC is at most BS square, then for every f and for every f, D is at most FBS square. So FBS is fractional block sensitivity, which is a larger measure than BS. So this falls short of what we would ideally like to show. However, the best upper bound on D in terms of BS for all functions is cubic, and improving it to quadratic would be a major result and would settle well-known conjectures. Okay, so the techniques, our proof technique involves the lifting theorem by Goose, Pitasi, and Watson, proven in 2017. Broadly, roughly speaking, what they showed is that for a class of communication tasks, the naive protocol that I showed you, so protocol is communication algorithm, if you like. The naive protocol that I showed you that simulates a decision tree is pretty much an optimal protocol. Yeah. All right. So I'll stop here. So, did I have more time? How much time did I have? All right.
About 10 minutes.
Okay. So I made a mistake here, estimating how long I'm. So anyway, so yeah, I haven't included a lot of things in this presentation. I haven't told you the proof techniques that go into our proofs. I have told you I've mentioned one open question, namely whether degree is capital D is at most degree square for zebra functions. And I have a few more questions and approaches and directions to share. So feel free to get in touch and meet me outside. I'll be glad to talk. Thanks.
Questions?
Yeah, I can take questions. Yes.
Yeah, I also. I had a question about this slide itself. So the way you have worded it is, if for every function and every bipartition something holds, then you have a bound on depth. Would it be enough if the precondition holds for all subfunctions of the particular f that you're, or subfunctions or restrictions?
No. No. So Goose, Pitasi, Watson deals with composed functions where you compose it with an indexing gadget. So yeah, we need probably, like, certainly it will be enough for some suitably defined class of functions, but not, I think, the class of subfunctions of it.
No, the subfunctions of the composed function. That is not enough, is it? So you want to give a depth bound on f, and you're going to look at maybe f composed with some gadget. And then if subfunctions of that new f composed with gadget are easy, then does it go through, or not even then? Not clear.
Not clear. I'll have to think about it.
We said that the players will be able to simulate the entire decision tree. And so shouldn't the communication complexity be at most the size of the decision tree instead of the depth?
So let's say this is the decision tree that the players jointly simulate, and each variable is held by one of the two players. So let's say Bob has x1.
Okay.
And both of them will know at all times where they are in this tree. So they will at all times be some node of this tree. So initially, both of them are at the root.
Okay.
And then there's an understanding who holds which bit.
Oh,
So Bob tells Alice that, Alice, x1 is 1. And then both
Okay.
of them know that they are at x3 now, and so on.
sure.
So can you give a high level idea of the proof of why decision tree complexity is at most this BSS square for zebra functions? Like,
So that's an adaptation of the proof that decision tree complexity is at most bs cube for all functions. And so for zebra functions, we could sort of adapt that argument and extract an improvement. And that improves that involves some additional complexity measures like certificate complexity that I talked about but didn't define. So maybe I can tell you offline.
Yeah, thanks for a nice talk. Stupid question, perhaps. Is there any relationship between the degree of F and the block sensitivity, or are they unrelated in general?
Well, their lower bounds on capital D and their capital D is upper bounded by cubes. So they are polynomially related. Yeah. And yeah, optimal polynomial relations may not have been worked out. Yes.
For communication complexity, are there better bounds known than the cubic bound
For
in terms of degree and block sensitivity?
Had there been better bounds known, that would have, by means of our result, translated to bounds on capital D.
Okay.
But for capital D, cubic bound is the best that is known. So.
Okay.
I have a question about the definition of the zebra function.
Yeah.
Could you go to that slide? Yeah, is the function like on each monotone path from 0 to the n to 1 to the n, the function undergoing the same number of alternations, is that equivalent to having the striped kind of a thing?
Yeah, so you can prove it formally, but the rough intuition is that if the function induces such sort of this kind of a striped structure onto the hypercube, then any monotone path will cross equal number of stripe boundaries, and those are exactly where the function value switches.
No, I'm saying, does that have to look like this? Like, could
Yeah.
it not be that it only like there's some path that changes at the end and some path that switches that flips value at the beginning or something?
So that could happen. So for instance, maybe follow my laser pointer.
Yeah.
There can be a stripe. So this shaded stripe could have instead, the bottom boundary could have, for instance, been like this.
Oh,
So
okay,
some
okay, I
part would
see.
have crossed this boundary earlier on, some parts would have crossed it much later. And so.
Okay. That helps. Thank you.
Here.
So I want to follow up on this question about D atmos BS square for zebra functions. Can you go to that slide? Yeah, so you mentioned it follows this outline of D atmos BS cube, which goes via certificate complexity.
Yeah, certificate times BS.
But somehow that second line gives an indication that that shouldn't work, right? If you can show.
No. So yeah, so I wanted to say that say this. So so I have some slides after my last quote unquote last slide. Oh, sorry. So we define a measure called maximin certificate complexity, which is, roughly speaking, the minimum certificate of any point. So this is, this is only if you, I'm assuming that this question will make sense only if you know the definition of certificate complexity. I haven't defined it. Yeah. So capital D is at most certificate times block sensitivity. We adapt that proof and show that it's at most this measure that we define, which is a smaller measure than certificate complexity, times block sensitivity. And we show that for the special case of zebra functions, this measure is at most block sensitivity. So you get BS square.
Thanks.
So just one question. I was just wondering about decision tree complexity in terms of if you're only interested in approximating this Boolean function,
approximating that,
Yeah,
which
so
says it's a 0, 1 valued function. So
yeah, I know, but suppose I just want it. I just want to compute it correctly for say 2/3 of the inputs. What kind of work is there? Like are there results about this?
so there are randomized decision trees.
Okay.
But the guarantee that they offer is that for every input, you will output a correct answer with probability at least 2/3.
Okay.
That measure is polynomially related to capital D. So
All right.
so randomization brings only polynomial advantage.
I see. Okay.
In this model.
Sure. Sounds good. Thanks.
So BPP is equal to P in this model. Here.
Right. Okay. Any other questions? All right. So if there are no other questions, let's thank the speaker again.
Thanks.
No setup.
All right. So our second talk is about randomized and quantum query complexities of finding a king in a tournament. Speaker is Nikhil Mande.
Thanks, Karthik. So now having heard Swagato's talk, I hope all of us know some query complexity. Therefore, I'm going to skip some of the basics and use that time to maybe unorthodoxly give you a story. And if you're a PhD student or a student in the crowd, hopefully this gives you some motivation for attending conferences and talks. Yeah, so this story is the story of how this work came to be. And it begins at last year's FSTTCS in IIT Madras, where there was a session on approximation algorithms, which is not my area of expertise. And the first talk I saw the schedule was a talk called, whose title was, When the King Comes at You, You Best Not Miss. And I thought, okay, I like The Wire and all, but I mean, I don't see how this is relevant to me. But then the chair of the session was Rakesh Venkat. He convinced me, he said, no, come to this talk Monday. It's actually a query complexity talk. You'll probably enjoy it. You'll find some questions. And I ended up going to that talk. It was by Chaya Trehan. It was a nice talk. And Chaya spoke about query complexity of kings in a tournament. For now, you don't need to know what that is. And if you were there in that talk, and if you have an extremely good memory, at the end, I asked this question to Chaya, what about the randomized and quantum query complexities? And she didn't have an answer. She didn't know. And so after the talk, Nitin Saurabh, who's also in the audience here, him and I, we contacted Manasvi offline. And what I'm presenting today is the answer to that question. So yeah, so it's joint work with Manasvi and Nitin. Thanks for bearing with the story. All right, so here's the outline. I'm going to tell you what kings in tournaments are in the first part of the talk. I'll tell you our results, sketch of our results, our proofs, and then summarize with some open questions. Yeah. Good. So what's a tournament? A tournament is a complete directed graph. So let's say you have n vertices. In this case, on the slide, n is equal to 5. It's a complete graph. And every edge additionally has one direction. So what you can view this as is, you can view it as there are n different teams, each of them play each other. And for each pair of teams, one of the teams wins a game, one of the teams loses a game. And the edge direction somehow indicates which is the winner, which is the loser. Okay? So an edge between V5 to V1, think of it as indicating in the match between V5 and V1, V5 won the game. Yeah, good. No ties. Yes, correct. So we assume there's either a winner or a loser. Good question. Thanks. And the goal here, I've deliberately put this in quotes, is to find a winner of the tournament. Now, what's the natural notion of a winner, you may ask? So let's assume one team wins all of their games. Then you'd imagine, okay,
this team is clearly a winner of the whole tournament. But of course, this need not be guaranteed. So there may not be such a winner, or in other words, there may not be a source in the tournament. Yeah. And there's been some work around defining what's a good notion of winners in tournaments, and king is one such notion. And kings were okay. I'll come to it in a bit. So a vertex V is a king in a tournament if for all other vertices one of the following two properties holds. Either there's a direct edge from V to W, or there's a length 2 path from V to W. So there exists an intermediate vertex U such that V defeats U and U defeats W. Okay. So in other words, V two-step dominates the whole graph. Good question. So length 1 path would be the most natural notion of a king, or of a winner, but there need not exist a vertex with that property. So the next step is to generalize length 1 to length 2. And as it turns out, every tournament has a king. So we don't need to go further. Yeah. And here's a proof. It's very simple. So it fits on the remaining part of this box here. That's nice. And this proof is due to Landau, who, as far as I can make out, Landau is the one who defined kings. So Landau was a mathematical biologist. And this appeared, I think, in the journal of, Bulletin of Mathematical Biophysics. And the name of the title of the paper is also interesting. It's on dominant structures in animal societies. Okay? So his motivation was like, let's consider a flock of chickens, for example, and then they have pairwise fights between them, and then you want to determine which is a most dominant chicken. I'm not making this up. I mean, there's a future reference. I'll come to it. Yeah, the title of that paper is The King-Chicken Theorem. So yeah. All right. So here's a proof that every tournament has at least one king. So we're going to prove this constructively. Consider a vertex of maximum out degree. I'll claim that this vertex has to be a king. And so n plus v is a bit of notation. N plus v is the out neighborhood of v. Okay. So let S be that set. And towards a contradiction, let's suppose that V is not a king. So there is a vertex W that is not two-step dominated by it. So what does this mean? If it's not two-step dominated by it, that means there's no edge from S to W, right? Because otherwise V would have dominated W via S. Yeah? So that means there's an edge from W to X for all X in S. And also V does not defeat W directly. So there's an edge from W to V, right? So this means the out degree of W is at least D plus 1 because the size of S is D. But we assume that V is a vertex of maximum out degree. So this is a contradiction. So yeah, that proves that every tournament has at least one king. There's been a lot of work on how many kings can a tournament have and so on, but it's slightly beside the point for today's talk. Good. So query complexity, even though you heard some setup in the previous talk, maybe I'll just go through it in this setting once more. Maybe it's a slightly different formulation, but it's the same object that was considered in Swagata's talk. So now your input is going to be the orientations of a tournament. So a query algorithm knows the number of vertices or the number of players in the tournament, and the edge directions are unknown. And what an algorithm is allowed to do is it can query an oracle. It can say, here's team I and team J. Please tell me who's the winner between team I and team J. And in other words, what's the direction of the edge between I and J? This can be done at unit cost. And all other operations are free for this algorithm. It can do internal computations that doesn't depend on the tournament for free. This is the main abstraction from the usual Turing machine. Good. So here's an example of a run of a query algorithm. Initially, you start with a tournament on 5 vertices, let's say, where you don't know any edge directions. an algorithm may decide, let me query the edge between V1 and V2 first. The oracle tells you that it's in this direction. At this point, the algorithm does some internal computations which are free, and then decides, I want to query V1 and V3. At this point, the oracle says, this is the direction. And then this carries on. And at some point, you don't need to query the remaining edges, because the algorithm realizes, with the information I have so far, I've already determined a king. And this is such a point because if you look at V4 here, so V4 dominates V5, it dominates V1, it dominates V2. And it doesn't have a direct edge to V3, but it dominates V3 via V2 or also via V1. Yeah. So there is a length path from V4 to all other vertices. So V4 is a king here. And the number of queries made in this case is the number of colored edges, which you can count. But, and the cost of this algorithm is the number of queries made in the worst case. So overall adversaries in some sense that reveal the tournament structure to you. Good. And we're interested in minimizing this cost. So that's the query complexity of solving kings. Good. So that's deterministic query complexity. What's the setup in randomized and quantum query complexities? Okay, so first, formally, king is modeled as a relation. So your input is 0, 1 to the n choose 2. So think of this as you have an n vertex graph, n vertex complete graph, and each pair of edges corresponds to a variable. So the value of that variable determines which direction the edge is pointing. So your input now is in 0, 1 to the n choose 2, and your output has to be a vertex, one of the vertices. So that's output is an element in square bracket n, and the output is supposed to be a king. So t comma v, formally it's modeled by this relation that's on the slide here. Yeah. Now a randomized query algorithm, in addition to making simply making queries, it also has access to let's say it has access to a coin that it can toss on its own as many times as it wants, and all of these randomness invocations are free. And the correctness requirement changes a bit, which I'll get to in a bit. A quantum algorithm, it's going to be tough to define in the scope of this talk, but roughly speaking, what it can do is not only can it toss coins and make queries based on the outcomes of these coins, it can also make queries in superposition. So this is like the output register here, the query outcome register, if you may. Yeah, so it can query edges in superposition. It can apply tournament independent, like the input independent unitaries for free. And then in the end, it makes a measurement. Yeah, happy to talk to you offline about this. Yeah, so the correctness requirement for randomized and quantum algorithms both is a correctness requirement for all possible tournaments. So your algorithm must have the property that no matter what the input tournament was, the algorithm correctly outputs a legitimate king with probability at least 2 by 3. Okay. Good. And the notation I'm going to use is D of king is going to be the deterministic query complexity of king. R and Q denote the randomized and quantum query complexity of king. Yeah. So a little bit about known results. I mentioned some slides ago, this proof of Landau that a vertex of maximum out degree is a king. Now, you may say, okay, if you want to find a king, why don't you just find a vertex of maximum out degree? Turns out this is hard. So there's a result from 25 years ago or so that says to find a vertex of maximum out degree, you essentially have to query all edges, all edge directions. Then there was this work of Shen, Sheng, and Wu from around 20 years ago that gives an algorithm that's better than the brute force algorithm of n square, n choose 2. Polynomially better than that, in fact, n to the 3 by 2. And there's a non-matching lower bound of n to the 4 by 3 that they also give. And there are a few more bullets here, but this is state of the art. If you're looking. I believe so. Yes. Yes. So that's one thing that we include in the paper as well, but I'm not talking about it. Yes, you're right. Thanks. So if you just care about the deterministic query complexity of finding a king, this is state of the art. It's been 20 years. I think it's a problem that can be solved. We're still working on it. Good. But there's been some progress in other directions, and here's some of them. So there's this paper from a few years ago, and by Biswas et al. And then they show several other results as well, interesting results about kings. But here's one of the statements that they show to be true. So if you want a vertex that does not two-step dominate, that does not necessarily two-step dominate the entire tournament, but you just want a vertex that defeats at least half of the other vertices via length 2. I mean, so it's a half king, you may say. If you just want such a vertex, then you can do it in order n to the 4/3 queries. So this matches the lower bound in this case. And then there was this work that from which the current presentation started at last year's FSTTCS. And this paper showed that the previous result can be generalized a little bit. If you want a vertex that dominates slightly more than half of all of the other vertices via length 2, then this can also be done in order n to the 4/3. Okay. And somehow the randomized and quantum query complexities were not studied at all. And the next slide is going to have our main results, and they fit in a very few characters. Yeah, good. So the randomized query complexity of king is, so tildes ignore polylog factors here, so let's not care about them for this talk. We'll care about them tomorrow. So the randomized query complexity of king is essentially n, which is a square root in the number of inputs. And the quantum query complexity is essentially square root of n. Good. So somehow it's much easier to analyze the randomized and quantum query complexities in this case than the deterministic query complexity. And this is not always the case for general functions or relations. Yeah. So I want to sketch a little bit of the proof. So to do that, here's two key lemmas that we need. The first one is due to Maurer, and this is the paper I was talking about. So this is a popular science article called The King-Chicken Theorems. Look it up, it's fun. And this somehow revitalized the interest in the community of studying kings and tournaments and such. Yeah. So this statement says, for an arbitrary vertex V in your tournament, consider its in neighborhood. So all the vertices that are not its out neighbors. Now, if you just restrict to the tournament induced on those vertices, a king there is a king in the whole tournament. Okay. So again, for an arbitrary vertex V, a king in its in neighborhood is a king in the whole tournament. Right. So before I prove it, let me tell you like some intuition as to why this is useful. Yeah. So let's suppose you can find a vertex that has very large out degree. Yeah. So now you can apply this lemma. I can get rid of all of its out neighbors, only focus on the tournament induced on its in neighbors, find a king there, and now you basically iterate or recurse, and now you've gone to a much smaller subproblem and repeat the process. Yeah, good. So why is this true? Again, this is very simple. It's going to fit in the next few lines. So let's consider a U to be a king in the in neighborhood of V. So we want to show that U dominates all vertices in the tournament via paths of length at most 2. Yes? Good. So in the in neighborhood of V, obviously U is a king by assumption, by this line here. So for all vertices in that part, U2 dominates them. And for all other vertices, by definition, they are in the out neighborhood of V. Okay, so U goes to V by definition because U is in n minus V. And for all other vertices, they are by definition in the out neighborhood of V. So U is in the in neighborhood of V, so U goes to V. And all other vertices are in the out neighborhood, so V goes to W. Yeah, good. Right. So this sort of suggests a recursive or iterative algorithm where you just try to prune your tournament by finding vertices of high out degree and so on. And indeed, that's what we do in our randomized algorithm. I'll admit that our randomized algorithm is not very hard. So the first observation is this. We need that if you randomly select a vertex in a tournament T, with high probability, it has linear out degree. Yeah. And as with many proofs I've already presented, it's going to fit here. Why do you expect this to be true? Some of you may already see it. This is just by a simple counting argument. So if you sum up over all vertices, the out degrees of those vertices, that's going to give you the number of edges in the graph, which is n choose 2. So a total of n vertices must contribute to a total out degree of n choose 2. And then some very simple counting, you take out a pen and paper, it will work out that with high probability, a vertex has linear out degree. Good. So some of you probably already see the randomized algorithm, but it's here on the next slide. Pick some vertices of V uniformly at random. These numbers are just for error amplification purposes, because error reduction purposes, sorry. So pick some vertices uniformly at random. We expect that one of them has very high out degree. So if none of them has high out degree, then output a random vertex overall. And that's your output of the algorithm. Otherwise, consider a vertex that has large out degree, remove its out degree, restrict your attention only to the in neighborhood, and apply the lemma that we saw on the previous slide. So find a king in the in neighborhood. Yeah. And then you repeat this until the tournament you're considering has square root n vertices. At this point, you can brute force because there's only n edges remaining. Yeah. Good. So a quick analysis. Each iteration, now if you want to compute out degrees of vertices, so computing the out degree of every vertex takes n-1 queries, right? Computing the out degree of a given vertex takes n-1 queries. And we've done some log n random vertices. That's so n times log n for this whole loop here. The number of iterations is order log n because the size of your vertex set is reducing by a factor of 1/10 each time. And therefore the total query complexity is O tilde n. Now there's some error analysis that's left to be done. So you just bound the probability of failure in each iteration, and the failure probability, by that I mean the probability that none of the vertices you've chosen in this loop has high out degree. And by the other observation on the previous slide, this probability is very low. Right, so that's a rough idea. So this gives you a total bound of order n. And now if you have any exposure to quantum whatsoever, and you see our main result, like we say randomized bound is order n, quantum bound is order root n. Say, okay, where's the Grover? Where's the amplitude amplification? And it's coming up. So here's the quantum algorithm. I just pasted the randomized algorithm. And I struck out a line that's problematic. So if in our quantum algorithm, we want to compute the out degree of a particular vertex, even in the quantum setting, unfortunately, this takes n-1 queries. You cannot do better than this. So what we have to do is we have to compromise here. We have to approximate the out degrees of vertices. This can be done classically, but yeah. So you can approximate it to some decent precision. Now there's another problem. Now we no longer know the in neighborhood of a vertex. So if I've approximated the out neighborhood of a vertex and my algorithm tells me the out neighborhood is linear sized, I know that its in neighborhood has dropped a constant fraction of the total number of vertices, but I don't know the in neighborhood itself. Okay. And now this is where we need a bit of technicality. And so what we can do here So I'm going to very quickly skim through this. You need a bit of quantum details set up to understand this properly, but yeah. So what we can do is you can use a single quantum query to mark the in neighbors of V. This is do it over a uniform superposition over all vertices. So think of the first step right now. What this means in some sense is you can set up a distribution such that if you sample from this distribution, you're going to get an in neighborhood of V with probability proportional to the size of the in neighborhood. Okay. But that may be too small. So what you can do is you can do amplitude amplification, expected. And this somehow gives us our quadratic speed up. And no worries if you didn't follow. So there's another difference that we repeated in the randomized algorithm, this loop, until our vertex set had size square root n, because at that point we could brute force. In the quantum algorithm, we really need to go until the vertex set is small, because we really don't know what the set of vertices remaining is, because we don't know what these in neighborhoods are. Another issue you might point out is how do you go to the in neighborhood if you don't know what it is? We use similar tricks to what we did here, and these tricks allow us to effectively sample from the in neighborhood of a vertex, and that is what we need actually throughout here. We don't really need the in neighborhood itself. We need the ability to sample from the in neighborhood, which we can do from quantum effectively. That's the key point, basically. Good. Yeah, and then if you work it out, this magical amplitude amplification has made all the n square root n. Wonderful. Yeah. Okay, good. Good. Yeah. Good question. Thanks. So when I mean O of 1, I mean it's less than equal to a constant below 1. So like 1/3. Think of 1/3. Yeah. So I didn't see. Yeah. So I do want to sketch the lower bounds quickly. Yeah. So fix a tournament T, an arbitrary tournament. And now I'm going to define different edge sets. So n different edge sets. So for each vertex V, I'm going to define EV to be all of the edges that are incident on V that need to be flipped in order to make V a source. So let's see a figure. So I don't know if you can see, but these two edges are colored differently, V5, V1 and V4, V1. So this constitutes EV1, because if you flip these two edges, then V1 becomes a source. Okay. And now a source is very easy to see is a unique king in a tournament. There can be no other king. Good. So EV2 is going to be V1, V2, V2, V5, and V2, V4. And then you can look at these EVs for different Vs in the tournament. And with a little bit of staring, you'll realize that all of these EVs are pairwise disjoint. Yeah. So essentially, an edge appears only in E of one of the endpoints. It cannot appear in both, and it can't appear in other EVs either. So we are going to give a reduction from the search problem, instantiation or a special version of the search problem, where you have an n-bit string, and it's promised that exactly one of the input bits is 1, everything else is 0. Find the 1. Okay. So it's well known that the randomized query complexity of this problem is omega n. The quantum query complexity is omega root n. So here's the reduction. You're given an input string x of the form that I described. It has a Hamming weight 1. Now I can construct the tournament corresponding to flipping the ith bit or the ith vertex edges. Okay. So flip EVI, basically, if I is equal to 1, xi is equal to 1. Yeah. So you construct this tournament, which is TVI. And now observe that if you want to query any of the edges in TVI, all you need to do is you need to query a corresponding bit in X. So basically, you can this is a legitimate query reduction. In other words, that a lower bound for finding a king here implies a lower bound for finding for the search problem. And like I said, finding a king here, all of these TVIs have unique kings. So yeah. Anyway, so you get lower bounds by a reduction from the search problem of omega n and omega root n on the search problem. And by our results, these are up to polylog factors, these are tight. Okay, so here's a quick summary. This problem of finding a king in a tournament, the best known bounds in the deterministic case, there's a gap between the best known lower bound and best known upper bound. Both of these are from over 20 years ago, and it's very interesting to close this gap. We settled the randomized and quantum query complexities up to polylog factors. We suspect we can get rid of this polylog factor, by the way, but it's not very relevant. So here's some open questions. Of course, what's the deterministic query complexity of finding a king? That's probably the most important or interesting open question that still remains. Unfortunately, we haven't made progress. And now here's an interesting promise case. Suppose I promise you that there are exactly 3 kings in the input tournament. Now can you find a king? So a simpler question is, let's suppose I promise you there's exactly 1 king. If you think about it a little, this is equivalent to the promise that there is a source in the tournament. And now if I promise you that you have a tournament with a source, you can come up with an algorithm of order n queries, like 2n queries that finds the source. So there's an order n algorithm if for tournaments with 1 king. What about 3 kings? Tournament with 2 kings are not possible. This is, again, it would have fit on here, but okay. And that's it. Thanks.
We have time for just one question.
Can you go back to the slide before the quantum part? So here we pick log n vertices. By increasing the number of vertices, can we make this probability, the success probability, high probability?
Yes.
Like 1 minus 1 by n.
Yeah. You can do that at the cost of log factors. Yes.
Okay.
Yeah.
And also, like, how many maximum kings can be there in a tournament? Is there any bound?
A good question. So for all n except 2, so for all I equal to 1, 3, 4, 5 up to n, there can exist I kings in a tournament. So there are tournaments with I kings.
Okay.
Sorry? Yes. So 1, 3, 4, 5, 6, 7. No. For I equal to 2, you cannot have a king. Yes. Yeah. For all other values, you can have kings. Those many kings.
Thank you.
Yeah. In fact, a random tournament, all vertices are kings. This is another interesting fact.
I don't understand one thing about, like, if you have 1 king that you can find very easily, because you said if you're promised there's 1 king and you cannot have 2 kings, can I not, like, in some way first remove the king that I find and then induce a graph, and then, like, these tricks don't work to find 3 kings?
Finding a king itself is the problem, right? If you're promised that your input has 1 king, your input is very structured. So your algorithm really depends on that promise.
Okay, makes sense. Thank you.
Yeah.
Let's thank the speaker again.
Thanks.
What about the non-deterministic query complexity? After whatever you say, I wanted to say, look forward to seeing you next year.
Look on your face. I thought you were coming to ask him.
problem, namely
Session going on.
Oh, ITH would say that.
It's going on
All of
till now.
You can't get to the list. Oh, yeah, sure. In less than.
It was all time.
N times 1 minus epsilon. Yeah, that's right. N minus N over log N.
hello everyone. As you can see, there are lots of words in the title, but
Hello. Can you hear me out back? Yes. So let's start. So please be seated. So we'll start. Welcome to new session. So this session, the first talk is by Professor Vijay Vajarani. Somehow, unfortunately, he could not make it to come here. So he has recorded this talk and we will be playing that talk.
hello everyone. As you can see, there are lots of words in the title, but I assure you they'll all become clear by the end. But let me start at a very simple place, a very simple problem, namely the online bipartite matching problem. So think of a bipartite graph with n goods and n buyers, which contains a perfect matching. And the goods are sitting around 1 through n, and buyers come one at a time, and you immediately are told the edges incident at the buyer. These are the goods that the buyer likes, and the buyer should get one of these goods immediately and irrevocably. So let's say the first buyer is matched to this via the red edge to the third good. The second buyer is similarly matched to another good. And the third buyer comes and both the goods that she likes are already matched. So she goes unmatched. And that's a problem.
Whatever.
Thanks. Yeah, am I audible? Hi, everyone. So today I'll be talking about the online weighted facility location problem. This is joint work with Professor Rahul Vaze. So before I start talking about this problem, I'll need to fix this, obviously. Alright. Yeah. So before I start talking about this problem, I'll talk about the basic facility location problem. So the facility location problem comprises of a metric space. Okay. Yeah. So the facility location problem comprises of a matrix space, and the input would be a set of requests in the matrix space. The request would be points in the matrix space. So given this set x1, x2 up to xn of requests, we would have to assign these requests to facilities, and we would incur some cost in this process. The cost would have two components. One would be a facility opening cost, which would be some constant f for every facility that we open. And the other would be a distance cost. That is, each request would be assigned to an open facility, and the distance of the request to the facility would be the distance cost. So the total cost would be, let's say in this example, we end up opening 4 facilities. Then the total cost would be 4 times f plus this distance cost. And our objective is to minimize the total cost. We would have to allocate the facilities so as to minimize the total cost. Next, I would like to talk about this online facility location problem. Here, instead of a set of requests, we would have a sequence of requests arriving in an online fashion. So let's say a request arrives, we would have to assign it to a facility. If no facility is open, we would have to open a facility for this. Let's say another request arrives and we assign it to the previously opened facility. Another request arrives and let's say it's far away, so we don't want to pay the distance cost. We open a facility for this request. So now for the previously opened request, it has a facility closer to it now, but we are not allowed to reassign it to this newly opened facility. That assignment was irrevocable. And our objective now would be to minimize the following ratio: the cost of the online algorithm divided by the cost of the optimal offline algorithm. This ratio is called the comparative ratio. If the online algorithm is randomized, then we will look at the expected cost of the online algorithm. Yeah. So I would like to talk a bit about the types of adversary that we will consider for this. So the first would be an oblivious adversary. So an oblivious adversary would decide on the requests, but it would also decide the order of arrival of the requests. So let's say the adversary decides on the following request and the following order. The algorithm would receive the request one by one. The first request arrives and it has to open a facility. The next request arrives, let's say it assigns it here. Another request arrives, and the last request, it again opens a facility. This is the oblivious adversary. This is in contrast to what we will call a secretarial adversary. The secretarial adversary would decide on the requests, but it cannot select the order of arrival of the requests. So it would take all the requests and it would, let's say, put it in a bag, and the algorithm would pick the request from the bag uniformly at random. So let's say this is the first request to arrive. The algorithm opens a facility. Another request arrives, it opens a facility, and so on. So these are the two types of adversaries that we will consider. So the previous results are, the previous results are the following. So Meyerson had proved that no online algorithm, sorry, can you? The previous adversary decides on the actual order of arrival of the requests. Here, the adversary cannot decide on the order of arrival of the requests.
going to be random or?
Yes, it will be uniformly at random in the secretarial model. Okay, so Meyerson had proved that no online algorithm can attain a competitive ratio better than log n by log n when we are considering an oblivious adversary. Yeah. So yeah, Meyerson had proved that no online algorithm can attain a competitive ratio better than log n by log n. He had also suggested an algorithm which was attaining a competitive ratio of log n. Later, Fotakis had given a more careful analysis of the same algorithm and shown that it attains the same competitive ratio. Meyerson had also shown that the same algorithm attains a constant competitive ratio against secretarial adversaries. No. So now finally, I'll be talking about the online weighted facility location problem. So yeah, here the input would be a sequence of requests, but the requests would also have a weight associated with them. So now, when a request arrives with a particular weight, we may decide to open a facility. The facility opening cost is still the same. However, if we are assigning it to a facility, if we are assigning the request to a facility, the distance cost is now multiplied by the weight of the request. So the total cost would be the total number of facilities opened plus the weighted distance cost. This is the online weighted facility location problem. Now I'll describe our results. So the first thing that we showed is that if we are considering an oblivious adversary, then no online algorithm can attain a competitive ratio better than omega n. Now notice that a competitive ratio of order n is trivially achievable by opening a facility at every request. So there is not much to study here. The next thing that we observe here is that if we are looking at the secretarial model, then no online algorithm can attain a competitive ratio better than omega log n. And then correspondingly, we show an upper bound where we show an algorithm which attains the same competitive ratio of order of log n in expectation. Throughout this talk, I'll only be describing this upper bound. Any questions so far? Okay. So I'll now describe the algorithm. Yeah. Yes, yes. So yeah, we work with a star metric space, but then we also show that the star metric space can be reduced to R2. Same as the lower bound for Meyerson's problem. Yeah. So yeah, we will now look at the algorithm, and the way I'll describe the algorithm is via an example. Let's say at any point we have a few open facilities and a request arrives. When a request arrives, it has a weight associated with it. What the algorithm would do is it would find the nearest facility to this request. If the algorithm decides to assign this request to the corresponding facility, then the cost would be the distance multiplied by the weight. Now, what the algorithm would do is it would look at the number line, it would look at the facility opening cost, and it would compare this cost of assigning, the distance multiplied by the weight. If this assigning cost is more than the facility opening cost, then it would open a facility. And if this assignment cost happens to be less than the facility opening cost, it would still open a facility, but with probability the assignment cost divided by the facility opening cost. So this distance multiplied by the weight, this is the assignment cost, and this ratio is the probability with which we open a facility. This is the algorithm. So this is the basic generalization of Meyerson's algorithm. So now I would like to spend some time on analyzing this algorithm. Before we analyze it, I'll mention a few lemmas that are necessary. These are lemmas from previous results, and I'll not be going into the proof. So the first lemma is the following. Let us take the set of requests that will arrive, and we know that there's an optimum way of assigning this request to facilities. Let's say that this is the optimum facility assignments. Now, look at any optimum facility and look at the set of requests that are assigned to this facility. We will call this set of requests as a cluster. So here we would have, let's say, 3 clusters. The first cluster has, let's say, 2 requests to it. The next one has 4 requests. This one has 6 requests. What the lemma says is that consider any cluster. And now consider the expected cost of the algorithm, of the online algorithm, divided by the cost of the optimal offline algorithm over this given cluster. Compute this ratio for every cluster. The worst ratio of a cluster would give us the upper bound on the competitive ratio. So what this means is that it would be enough to analyze one cluster. If we can analyze all the clusters individually, we would have a bound on the competitive ratio. The next lemma is the following. It says that, let's say we have an input arrives with a given weight, and this is the online facility that is available to it. If we decide to assign this request to the facility, the cost incurred would be the distance multiplied by the weight. However, we may not always assign it to this facility. We may decide to open a facility. What the lemma says is that the expected cost is twice the assignment cost. So we will not be opening facilities too often, and the expected cost would at most be twice the assignment cost. Now, another way to look at this lemma is that it says that having a facility near the optimal offline facility is good enough, because let's say we have a request, we have an online request such that the distance of the request to an online facility is of the same order of the distance of the request to the optimal facility. If these two distances are of the same order, then the expected cost would be of the same order of the cost incurred by the offline optimal algorithm. This is our lemma 2, and we will just need one more lemma. It says that let us look at any subsequence of requests, and let us see when is the first time that we open the next facility. So the lemma says that the next time that we open a facility, we would have incurred a cost of about f, less than f, by the time we open the next facility. These are the 3 lemmas that we will use. We will be skipping the proofs of this. Now we will go on to the analysis. So let's say that the following would be the set of requests arriving, and we want to compute the competitive ratio. So the competitive ratio is the following: the expected cost of our algorithm divided by the cost of the offline optimal algorithm. So the cost of the offline optimal algorithm can be computed via this assignment of the facilities. And now what lemma 1 would say is that it is enough to just consider each of the clusters individually. So we can just study each of the clusters individually and we would be done. Now we also know that opening a facility near the offline optimal facility is good enough. So if we end up opening a facility somewhere here, we would be somehow good. I'm just speaking a bit vaguely here. So this would somehow tell us that the order of arrival matters. Let's say that the first request to arrive is the one closest to the offline optimal facility. Then we would have a facility close to the offline optimal facility. This is somehow good for us. And if the request to arrive first is a request which is far away, we would have to open a facility for this. Then another request would arrive far away, we would again have to open a facility, and somehow we would be unlucky. So this gives us an intuition that we want to study the order of arrival of the requests. In order to understand this, we would define something called phases in a cluster. So since this is a cluster, they would all be assigned to a single facility. So we will start with phase 0, and we would change the phase every time a facility is opened closer to the offline optimal facility. So let's start with phase 0, and let's say this is the first request to arrive. Let's say we open a facility, the phase would change to phase 1. Next, let's say that this is the next request to arrive and we did not open a facility. The phase still remains the same. Another request arrives far away. Let's say we open a facility, but again, the phase would not change because we already have a facility closer to the offline optimal facility. So the phase would not change. Let's say another request arrives and we end up opening a facility. Now this facility is closer than the previously opened facility. So the phase would again change to phase 2. Let's say another request arrives and this is even closer. We open a facility, the phase would again change. There are still a bunch of requests that are left to arrive, but the phase would not change even if we end up opening a facility there. This is the definition of phases. Now, why are we looking at phases? It's because of the following lemma, which says that if the arrival order is such that if the arrival order and our algorithm's random choices are such that we end up having k phases, then the cost ratio over this cluster would be of the order of k. So clearly, if we get an estimate on the number of phases, we would have a bound on the cost ratio. So how to estimate the number of phases? So this is what we'll prove next, that the expected number of phases is of the order of log n if there are n requests in a cluster. Okay. So any questions so far? Okay. So in order to analyze the total number of phases, what I would do next is I would do a reduction. The reduction would be as follows. Let us assume that there are n requests in the cluster. We would look at a matrix of size n cross n. It would be a matrix of probabilities. So the first column would correspond to the request that is closest to the offline optimal facility. And the last column would correspond to the request which is the furthest away from the offline optimal facility. And the columns would be arranged in such a way such that each column corresponds to a request, and they would be arranged in a way of their distance to the offline optimal facility. The entries of the matrix would be probabilities. So initially in the first row, it corresponds to the probability of opening a facility if this is the next request to arrive. So initially, since there are no facilities available, no matter what request arrives, we would end up opening a facility. Hence, everything is 1. We would end up opening a facility with probability 1. Let's say another facility opens somewhere else in a different cluster. Now, this might influence some of the requests in this cluster to not open a facility and assign itself to this open facility. Hence, the probability of a couple of them went from 1 to something lower than 1. Then let's say another facility opens somewhere in another cluster and the probabilities change. Let's say finally a request arrives in this cluster, and this request corresponds to the following column. So we notice first that the entry in the corresponding row is 1, which means that the probability of opening a facility is 1 over here. So we would end up opening a facility. We know that this would change the phase. So what we would do in our matrix is we would delete every column to the right of this column. The reason we are doing this is because every column to the right corresponds to requests which are further away than this facility. So they would not end up changing the phase. So we would end up deleting every column to the right of this. We would update the probabilities, and then we would freeze the corresponding row, and we would start working on the next row, because we would change the row every time a request arrives. So let's say the next request to arrive is this one, and it is further away than the previously opened facility. So we end up opening a facility, but the phase would not change. Similarly, another facility opens, and now this is the request to arrive next, and we did not open a facility. Another request arrives, we did not open a facility. And let's say finally, the request closest to the offline optimal facility arrives. If we open a facility here, the phase would again change. But let's say we did not end up opening a facility. And finally, we end up opening a facility for the request that is the second closest. So since we are opening a facility nearer to the previously opened facility, the phase would again change. And we would again end up deleting the columns to the right of this. So this matrix would somehow help us in computing the total number of phases. So I'll describe this matrix as a selection process. So what would happen here is that at every time, an array of probabilities would arrive, and we would have to select one entry from this array. So the first time, the first row arrived. This was the array of probabilities. And we selected, and the array arrived along with an element in the array. And we selected the element with probability 1. This is what is written, that we select the probability, we select the element with the corresponding probability. Later on, similar such arrays arrive, but we will select the element with the corresponding probability, but only if it is to the left of the previously selected elements. So here, for instance, we would select an element, but only if it is to the left of this column. We would not select anything to the right of this column. This is because we know that the phase would change only if it is to the left. So we would select the element the first time it arrives, and then we would select the element with the probability, but only if it is to the left. And we have seen in the reduction that the total number of phases is the number of elements in the selection process. So the next thing that we can see is that the selection process would select order of log n many elements in expectation. This immediately tells us that the comparative ratio is order of log n. Okay. So I would just give a basic proof idea of this theorem. So the way I would explain this is the following. So imagine the matrix, and we will use the following lemma. So assume that at any row, there are k elements. Since we are deleting off columns one by one, the number of elements may not be n. So let's say that there are k many columns left. So if there are k many columns left, we will have two cases. Either the probability entries in the row are large, or the probability entries in the row are small. So what the lemma says is that if the probability entries in the row are large, then the next element that we will select is much towards the left, that we will delete off a lot of columns. And the other case is if the entries in the row are small, then the probability of picking the elements are small. Then we would end up throwing away a lot of rows. So what this lemma says is that every time we would, in expectation, throw away k by 3 many elements. This would end up giving us the order of log n many selected elements. Yeah, so I would just summarize what we have done. So these are the previous results for the unweighted case. It says that for oblivious adversary, the comparative ratio is order of log n by log n. And for the secretarial adversary, it is constant. For the weighted request, what we have shown is that the comparative ratio is theta n. And for the secretarial case, for the weighted request, we have shown that it's of the order of log n. That's it. Thank you. Any questions?
There is time for questions.
Your algorithm WRFL doesn't really use the knowledge of n, right?
Yeah, neither does Meyerson's original algorithm.
Okay, so
but we are allowed to use, but we don't use it. Yeah.
Okay.
So what is the factor in the unweighted case, secretary model, the constant
This
factor?
constant?
Yeah, exact factor.
It is 8. The
8.
last time I checked it, it was 8. Yeah.
Any other questions? I have a little bit one question, like what really changes when you go to weightage, because it becomes log n2 or n? Like, can you little bit throw insights what it changes? Like, why can't we absorb that weights into distance and then reduce it to unweighted?
Yeah. So you can think of the weights as entering the same request multiple number of times. So in the unweighted case, if you are to do the same, like give the same request over and over again, the number of requests as such blows up. So that is why if the number of requests blows up, n is larger and the comparative ratio becomes smaller. Here, we can give a smaller number of requests, but we can simulate this. We can simulate the weights using the smaller number of requests. That is why this is n.
Any other questions?
We did not actually use the total number of requests. Yeah, we did not use the total number of requests.
No more question. Let's thank the speaker again. We can head for lunch.
So if I about this Meyerson's lower bound, so it comprises of giving the same request over and over multiple times. That is something that we can simulate using this without doing the same impedance.
Can you turn on the mic?
Hi, Sharon. Can you hear us?
Yes, hi, can you hear me?
So how do we see her?
I think you can just stop share for now. That is fine.
Yeah.
And
Hi, Sharon. Can you hear us?
Yes, I can. Can you?
Yes. So 1 second, we're setting your audio. We can't hear you. So I think in the hall, we're trying to set the audio. Yeah. Yeah. Yeah.
for now, that is fine.
Can you speak?
Yes,
Hi,
can you
Sharon.
hear
Can
me
you hear
now?
us?
Yes, I hear you perfectly.
Yes. So 1 second, we're setting your audio. We can't hear you. So I think in the hall, we're trying to set the audio. Huh? Yeah. Yeah. Yeah.
For now, that is fine.
Can you speak?
Yes,
Hi,
can you
Sharon.
hear
Can
me
you hear
now?
us?
I hear you perfectly.
Yes. So 1 second, we're setting your audio. We can't hear you. So I think in the hall, we're trying to set the audio. Yeah. So yeah. So can you try now?
Yes, can you hear me?
This is better. Yeah. So yeah. So probably. Yeah. Yeah. Probably she can start sharing her slides as well.
Okay,
So
I'll do that.
hey. So good. Excellent. You want to try writing on it? Like it's okay. All good. All good from your end.
I think so. Can you see my screen?
Yes, we can.
Okay, yes,
Patricia,
then yes. And I hear you. Can you hear me now? I guess so.
Yeah. All good.
Okay.
Yes. So we have a bunch of mics that will pass around when people ask questions.
Okay, perfect.
All the mics so she can. Yeah, all the mics she can hear. So okay. So she could probably.
Then she'll get to see anything or from this camera? Okay.
Yeah. Okay. So that is a camera. Yeah, she can only
only
hear.
both of these.
Yeah. Only both of these mics, right? Three mics. Good.
So is she able to see us? Sharon, are you able to see us? This is Deepak here.
So I see the auditorium, but I see because of the screen share, I see it very small. So, I mean, I can see, but not really. I can't see faces or anything.
That's a camera also. Okay. So that's the camera which is going, is it? Okay. So those. Okay. Okay. So not this one. This is not.
I am Girish.
Oh, hi, Girish. Deepak. You guys have done a good job. Did you? We call some of the people and I don't know whether. This trailer will start in a few minutes.
And stop sharing for just a minute because I want to disable some notifications here. So just a second.
Hello, check. Hello, check. Okay.
Seen from next to the camera.
This one is it?
Yeah.
So which
I mean,
camera is?
So that camera is the one.
Okay.
Sharon can see you from this side.
Okay.
Now it's like
Okay, that's me. Okay. Hello, check. Sorry, we'll get started. Yeah. Okay, everyone, please settle down. We'll get started. So I am Deep D'Souza. I'm going to chair this session. And so it's a pleasure to have this talk delivered by Professor Sharon Shoham. Can you please settle down, please? So Sharon works broadly in the area of program analysis and verification, and she's contributed to many different things from techniques and deductive verification, logic solvers, model checking, and she's probably best known for her work in studying property directed verification, which is a kind of automated way of automating deductive verification based on Floyd-Ho logic. And she's probably best known for her work in that. And today she'll be telling us about her work in trying to understand why these property-directed verification tools do so well in practice. And that is from concept learning to SAT-based invariant inference. So Sharon, over to you and welcome.
Thank you. Thank you for the nice introduction. I was really excited about being there and giving this talk. So I really am very sorry that I couldn't eventually be there in person. but I hope we'll make it work. So I'll talk I will talk about some relation that we found between concept learning and SAT-based invariant inference. So first, this is joint work with Yotam Feldman, Neil Immerman, Muli Sagiv, and James Wilcox. And all the results that I'm going to talk about are basically part of Yotam Feldman's PhD thesis. The context of this talk is safety verification. So just to make sure that everyone knows what I'm talking about, in safety verification, we want to ensure that some bad behavior of a system never happens in any execution of the system. And examples could be, if we think about programs, it could be that there are no null dereferences. If we think about concurrent programs, then we may want to require that there is never a mutual exclusion violation. In distributed systems that need to reach, for example, consensus, we want to make sure that at most one value is chosen, and so on. So there are many examples. These are the most basic properties that we can think of that we would like to verify, but they're also very important. And in fact, actually, also more general properties can also be sometimes reduced to such properties. So really, this is a very central topic in verification. And to be a bit more concrete about the setting that I'm going to address, so we model systems using transition systems. And in this talk, I'm going to talk about transition systems that are modeled using Boolean variables, the simplest kind of systems that we can think of. So here is an example. Suppose I have some system with n Boolean variables that encode some n-bit vector. And initially, all the bits are just 0. Then in my description of the system, I also have a transition relation, which tells me which explain the steps of the system. So here, for example, what my system can do is take this n-bit vector and increment it by some even number in every step. So we have these y1 to yn, they are just halved, they get some value, and we multiply them by 2 and add to the x1 to xn vector. So in every step, we increment the vector by some even number. This immediately defines some set of reachable states, all the states that I can reach starting from an initial state and executing steps of the transition system. So this is a set of reachable states. And in safety verification, I will also have some property that I want to verify. So for example, here, I may want to make sure that I may say that a bad state is a state where all the bits are 1. And my safety property could be that this state is never reachable. I can never reach it by executing the system. And here it's very simple to say that this is really the case. All the reachable states here are all even numbers. I started from 0. I always add an even number. I always stay with an even number. So I cannot reach this 1, 1, 1, 1, which is all. But how do I verify such properties in general? So a prominent way to do so is to find some inductive invariant. An inductive invariant is a set of states. Usually we describe it by some formula, but it's just a set of states that has to satisfy 3 requirements. The first one is initiation. It has to include the initial states. The second is safety. It has to be disjoint from the bad states. So it separates the initial states from the bad states. And the most interesting property is that it satisfies consecution, which means that if I start from a state inside this inductive invariant, then by executing a step of the system, I can never go outside. I never have transitions going from inside the inductive invariant to outside of it. So this inductive invariant is preserved by the steps of the system. And I write it like that with as this whole thing. So if I have such an inductive invariant, because because of initiation and consecution, I know that it is a superset of the set of reachable states, because the reachable states are just the smallest set that includes the initial state and is closed under transitions. And therefore, because of safety, I know that my system is safe. Okay, so I'm happy if I find such an inductive invariant. Let's look at an example for this simple system. So for example, I could ask myself, if I take all the states except for the bad state, except for 1, 1, 1, 1, is this an inductive invariant? So first it will satisfy safety and initiation. It separates the initial states from the bad states. But if we look closely, I imagine that you can immediately see that it doesn't satisfy consecution. Because, for example, I can start from some odd state that is not bad by itself. For example, the 0, 0, 0, 0, and 1 at the end. And by adding the appropriate even number, I can get from it immediately to the bad state. So this is not inductive. It doesn't help me to verify my system. But here is another example. Suppose that in my inductive invariant, I just say that the least significant bit xn is not 1, or in other words, I basically just say that the number is even. Then here it is easy to see that it is inductive, because if I have an even number and in a step I can only add an even number, I always stay with an even number. So I stay within the inductive invariant. Okay, so this is the concept of inductive invariant, and it's very important for this talk. Because what I want to talk about is invariant inference as a way to verify safety. So in invariant inference, what we want to do is to find such inductive invariants automatically. And more specifically, I'm going to talk about SAT-based invariant inference, where we use a SAT solver to help us in this process of finding an inductive invariant. And when we think about SAT-based invariant inference algorithm, usually what we do is we model all the components of the transition system, the initial states, the bad states, the transition relation, all of them are given to us by formulas. So we have some set of state variable x, and init and bad would just be described as formulas over these variables, and the transition relation formula would describe the transitions, the steps. And because steps involve two states, then this would usually be a formula over two copies of the variables. The unprimed copy is that you can see here. Sorry, it doesn't work well. X would be used to describe the pre-state of a transition, and X prime would be used to describe the post-state of a transition. So this is how I get the description of my system using formulas. And again, I want to find an inductive invariant, which is also a formula over these variables X. And just to give an example of how a SAT solver, a satisfiability solver can help us in this task, suppose that I have a candidate inductive invariant. I guessed some formula, and I'm asking myself, is this an inductive invariant? So I can at least check all the requirements using a SAT solver. For example, initiation, if you remember, was the requirement that the initial states are a subset of the inductive invariant. So using a satisfiability solver, I can check it by making sure that there is no state in the intersection of init and the negation of the inductive invariant, which is exactly checking unsatisfiability of the formula init and not I, if I is my candidate. And I can do it for the other conditions as well. So this is an example of how I can use a SAT solver to help me in the process. And indeed, in the recent years, there have been a lot of SAT-based invariant inference algorithms proposed, and they have been very successful. Basically, probably you all know, SAT is a theoretically hard problem. It is NP-complete, but there are also very good tools now that can handle formulas with a lot of variables, and I don't think there is a good understanding why they work well, at least for our domain of verification, but it turns out that they do. And accordingly, these tools that use a SAT solver also had a lot of success in practice. They basically revolutionized the industry in verification. So they are really, really successful in practice, but all the theoretical questions about them, all the theory about why they actually succeed or when do they succeed, can we say something about the complexity, why, when will they fail, and so on. All of these questions don't really have good answers, and they didn't get a lot of attention, actually. So this is what we wanted to do in the research that I'm going to describe. We wanted to understand SAT-based invariant inference algorithms, and we chose to do it from the perspective of exact learning with queries. So if you have a question now, of course, you have to first ask ChatGPT. So I did the same thing. I asked ChatGPT, are SAT-based invariant inference and exact concept learning related? And I got an interesting answer. So I got this answer. This is part of the answer, at least. It told me that they are related, but they operate in different domains. It also said that invariant inference is more specific and exact concept learning is a broader term. So really interesting. But I hope that even though this is a nice answer, I hope that you will find what I want to describe to you in this talk a bit more informative. So what I'm going to do is talk about results from 3 papers that we had on this topic. And the main reason why I even showed you this chat with ChatGPT was to say that ChatGPT and the learning that it employs is not the kind of learning that I'm going to talk about. I'm going to talk about a model of active learning, learning with queries. So more specifically, this is the learning model that I'm considering. This is classical learning. So the model is a model where we have a learning algorithm, a learner, that tries to learn some concept, an unknown concept. And for the sake of this talk, we can think about this concept as a formula. So just for a formula phi. And the learner can interact with an oracle that knows, the oracle knows the unknown concept phi. And the learning algorithm can ask it questions. For example, it can choose some candidate psi1 and ask the oracle, is this the concept that I need to learn? And then the oracle will answer yes or no. And if it answers no, it will also provide a counterexample, which can either be a positive example, some state that satisfies the concept phi, but doesn't satisfy the candidate, or a negative example, which is just the opposite. And given this answer, the algorithm can come up with another candidate, psi2, and again ask the oracle, is this the concept that I need to learn? Again, the oracle will answer. These kind of queries are called equivalence queries, but there are also other kinds of queries. So for example, the learning algorithm can also pick some state and ask the oracle, is this specific state, does this satisfy the concept that I need to learn, phi? And again, the oracle would answer yes or no. And this process, these kind of queries are called membership queries. And these kind of queries will go on and on until the learning algorithm actually learns the concept. So this is a model introduced by Englund for exact concept learning with equivalence and membership queries. Okay, and what I want to do is think about SAT-based invariant inference sort of in this way. I want to look at it as inference with queries. So there are some clear relations here. So now instead of a learning algorithm, I will have my inference algorithm. And the goal of the inference algorithm is to learn an unknown inductive invariant. So instead of just an arbitrary formula, I want to learn an inductive invariant for some program that I'm trying to verify. But then there is also, and the oracle, the teacher, is going to be a SAT solver. But then there is also a very important difference. And the difference is that in the exact learning setting, we assume that the oracle knows the unknown concept. So it can really answer questions about it. But we cannot assume that the SAT solver knows the inductive invariant. I mean, this is not realistic. This is not the setting where we operate. So what does the SAT solver actually know? What kind of queries can we ask it, and what do we expect it to know? So in the model that we define, what we assume is that the SAT solver knows the transition relation of the system that we are trying to verify. It knows the steps, basically. And we assume that the learning algorithm, the inference algorithm, on the other hand, doesn't know the transition relation. So it cannot access, the inference algorithm cannot access the transition relation directly. It can only access it by asking the SAT solver. And we think, and we also see that this kind of model actually captures the way most of these modern SAT-based algorithms use a SAT solver. They really never do anything with the transition relation themselves. Whenever they want to know something about the transition relation, it comes as some kind of satisfiability question that goes to a subsolver. So we believe that this is a good way to describe these, to capture these algorithms. But still, there's the question of what kind of SAT queries will we let the inference algorithm ask. And again, our goal is to capture existing realistic algorithms, because this is what we want to understand. If we can understand them as concept learning algorithms, then our hope was that we can also get some complexity results for them, because in the learning literature, there are a lot of nice complexity results. Okay, so now this gets me to the outline of the talk. So what I'm going to do in this talk, I want to think about invariant inference in comparison to exact concept learning. The first thing that we'll do is we'll define two query models for invariant inference, basically two kinds of queries that we allow the inference algorithm to ask the SAT solver. After we define these two query models, I will show some complexity lower and upper bounds for inference in this these models. Looking at the bounds, we will go back to the comparison to exact concept learning, and we will see basically that there are some significant differences between the problems. We'll show that in some sense, invariant inference is harder than concept learning. But also positively, we will show that despite this, despite being harder, we can actually sometimes derive complexity results for invariant inference from complexity results that are already known for exact learning. Okay. So let's start with defining query models for invariant inference. So the first model that we defined, this is basically the simplest that one can think of, is we call it the inductiveness query model. This is a model where what the inference algorithm can ask the SAT solver are inductiveness queries. So it can give it some formula alpha 1 and ask, is it inductive? It can give it some formula alpha 2, ask, is it inductive? And the Oracle, the SAT solver will answer either yes or no, and no will come with a counterexample. So more generally, this is what the Oracle can answer. It gets some alpha I, and the question that it is being asked is whether the whole triple alpha I delta alpha I holds or is valid, which means that is it correct that whenever we start from a state satisfying alpha I, satisfying the preconditions alpha I, and we execute a step of the condition, are we guaranteed to end up inside the post-condition alpha I, still satisfying alpha I? Okay. So this is the kind of query that we allow in this model. So first thing, note that this kind of query we can really ask a SAT solver to answer it, because checking this corresponds to checking unsatisfiability of this formula here. Is it true? We want to make sure that if I start from alpha I and I execute a step of delta, I cannot end up in a state satisfying alpha I. So this should be answered. Okay, this is the kind of queries. What about now the answer? So I said if the formula is inductive, the SAT solver will just say yes, that's it. But if it is not inductive, we want to get a counterexample. But note that here, what would be a counterexample? A counterexample would be actually not just a state, like in the traditional model of learning. Here, a counterexample is going to be a transition, a pair of states, such that the first state satisfies the precondition alpha I, but the post-condition, the post-state, the second state, does not satisfy alpha I. Okay, so what we have basically a transition that goes from alpha I to outside of alpha I. And this will be important. Okay, so this is the first model. And actually, this model already captures algorithms that belong to the ICE framework that was introduced in 2014. In the ICE framework, the learner is supposed to learn candidates from three kinds of examples: positive, negative, this is like the standard setting, but also implication examples. And as you can see, counterexamples to induction give us, these are basically transitions this is exactly what they give us. They give us implication examples, because when we have a transition, all we know is that if the pre-state of this transition satisfies I, then the post state has to satisfy I as well. That's it. We don't know if they are in the invariant, if they are outside of the invariant. We only know this implication. So this model fits in the inductiveness query model. But now the next question is, okay, so this is one query model. Is it sufficient to, and it captures the ICE framework, but is it sufficient to capture also other interesting SAT-based algorithm? Specifically, we're really interested in interpolation and IC3, property-directed reachability. So let's see an example of such an algorithm so that we can understand whether the model captures it or not. So I'm going to describe now an interpolation-based inference algorithm. So here is the idea. Okay, again, we want to learn to infer some inductive invariant. The idea is that we start from some candidate, I0, I call it here, and initially we can just take the initial states, and we can check maybe this is already inductive. If it is, we are done, we are happy. But if it is not, then we need to do something. What do we need to do? We can weaken the candidate to get a new candidate. And so originally, the interpolation-based algorithm was introduced by Macmillan in 2003, but I'm going to describe here a variant that was a bit more recent and was inspired by IC3 PDR, and it is sort of like doing model-based interpolation. So in the variant that I'm going to explain, what we are going to do is the following. So I is not inductive. It means that we have some counterexample to induction, some transition that starts in I and ends up in a state outside of I. Let's call this state sigma 1. So what we're going to do in a sense is essentially we want to weaken our candidate to also include this sigma 1. But before doing it, first we will check that this sigma 1 really cannot reach a bad state in k steps. If it does, then we actually have a counterexample here, but later it will be also a case of failure. So two things about that. First, note that checking this reachability, checking if from sigma 1 in k steps we can reach a bad state, this again can be done with a SAT solver. This is called the bounded model checking query, where we can actually encode exactly k steps of the transition system. And we can check it. So this is a SAT query. So we check that. And the second thing that I wanted to comment is that k is a parameter here. So I can choose different k's. But when I run the algorithm, I fix some k, which is like the length of the bounded model checking query that I consider. And I check whether the sigma 1 can reach a bad state. Again, if it does, I have nothing to do, I fail. But if it doesn't, this is the scenario that we are hoping for. If it cannot reach a bad state in k steps, then now we want to weaken the invariant, and instead of just adding sigma 1 to the candidate invariant, what we are going to do is first generalize it into a larger set of states that we are going to add to the invariant, and we do that by interpolating in a certain way. And we do that as long as the larger set that includes sigma 1 still cannot reach a bad state in the same number of steps, in k steps. And then we weaken the invariant with this interpolant. So how do we do this interpolation? How do we generalize from sigma 1 to a larger set? Let's look at the example from before, and I'll show you an example of how we do it. Suppose this sigma 1 step state that we got is the state 0, 1, 1, 1, and until 0. We can see in this particular example, because this state is even, we know that it cannot reach a bad state in any number of iterations. So our bounded model checking query will be fine. And now we want to generalize. So generalization is done by first we encode this state as a cube, a conjunction of literals, basically encoding all the literals that are true and false in this state. And we start trying to drop literals and see whether after dropping a literal, we still cannot reach a bad state. So for example, we can try to drop the first literal, saying that the most significant bit is 0. And if we do it, yeah, still none of the states that we get still cannot reach a bad state. So this is good. We don't need this literal, and we managed to generalize. And we can do it to the second literal as well. Again, this is fine, still cannot reach a bad state, and we can generalize. If on the other hand, in this example, we will try to drop the last literal, talking about the least significant bit being 0, then of course, then there is a state captured by this set that reaches a bad state. So we cannot drop this literal. So we have to keep it. But all the other literals in this example, we can just drop. And after dropping it, we get xn equals 0. And when we add it to our init, we basically get an inductive invariant. We basically get the formula saying that that the number is even. The least significant bit is 0. So we are like in this example, simple example, we are done basically in one iteration. And just to recap this algorithm, because we will also get back to it later. So this is the interpolation-based algorithm with parameter k. We start from some candidate, it can even be false. And as long as we have counterexamples to induction, we take the post state of a counterexample to induction. This here it's a state sigma prime, and we add this junction to the inductive invariant with its generalization. Well, the generalization is like in the example done by trying to drop literals from the encoding of sigma prime, as long as we still cannot reach a bad state in k steps. So here is the k, the parameter of the algorithm. And you can see that what we get here is invariance in DNS, because we basically encode the sigma prime as a cube and drop literals. So in every iteration, we will learn some term in an invariant that eventually will be in a disjunctive normal form. Okay, so this is the algorithm, and now let's go back to the inductive query model and ask ourselves if this model can discuss if the interpolation algorithm fits in the inductive query model. So we need to look at the places where the algorithm uses the transition relation and see if we can encode these checks as inductiveness checks. So the first place is here in the while loop, where we just check if our current candidate is inductive, and if not, get a counterexample to induction. This exactly fits in the model. Okay, this is an inductiveness query exactly. The second place is when we try to generalize, and we have these bounded model checking queries, checking that from sigma prime we cannot reach a bad state. And this doesn't immediately look like an inductiveness query. Okay. So not sure. Can we, can't we? Don't know. But so what we did now, we defined another query model, the whole query model that can capture this algorithm and others. And in the whole query model, we now generalize the kind of queries that we can ask. First, if before we could only ask inductiveness queries, which meant that we talked about the same precondition and postcondition. So here we talk about whole queries where we ask if starting from precondition alpha I, we will always get to postcondition beta I. So the pre and postcondition can be different. And we also have this parameter k here. We can ask about k steps of the transition system. So this is the model. And note that here counterexamples will now be if this triple doesn't hold. Sorry, again, we can encode it as a bounded model checking query and so on. And here, if it doesn't hold, a counterexample will be a trace that consists of k steps or k plus 1 states, where the first state satisfies alpha I, but the last state in this trace falsifies the postcondition beta I. And like I already said, this model, we checked and we saw that it is capable of modeling several interesting algorithms. For example, the interpolation algorithm that we showed earlier fits in this model. So first, the inductiveness query, of course, still remains also a valid query in this model, because this model allows just more general queries. And now this bounded model checking check, we can also think of it as a whole query, because making sure that that from sigma prime, we cannot reach bad in k step is the same as making sure that if we start from sigma prime and take k steps, then we have to end up in not bad. we cannot reach bad means we have to end up in not bad. So this is a query, a whole query. So this is good. And I will also mention that we can also capture IC3 using this model. Okay, so these are the two models that I wanted to talk about that we introduced. And I want to talk about some complexity results for these query models for invariant inference. So the first result that we had is that if we consider the whole query model, the more general model, then we have a lower bound, an exponential lower bound on the number of queries that we need in the worst case to infer short DNF for invariance. So we consider formulas in DNF. This is a very general and rich form, but we are interested in learning or inferring short invariance of polynomial length. And we think we need an exponential number of queries. And I want to emphasize that this lower bound holds even if we let the inference algorithm have unlimited computational power. And it is an unconditional lower bound. It doesn't depend on the complexity of SAT or anything like that, because it actually follows from it's an information complexity bound. It results from the fact that the inference algorithm cannot access the transition relation directly. It can only do it through the whole queries. And I also want to say that throughout the talk, I'm going to be interested in inferring short invariants, because if there is no short invariant, then we don't really have any hope to find it. So even if I don't say it explicitly, that's what I mean, that I'm interested in short invariants. And another comment that I want to add is that this lower bound holds even if we restrict the class of inductive invariants that we are trying to learn into a smaller class, which is just monotone invariance in monotone DNF. Monotone means that the variables can only appear positively. So this could be a simpler problem, but actually the lower bound holds for this as well. Okay, this was a general lower bound for the whole query model. But now the next thing that we wanted to do is really compare the two models to understand the relative power. And what we managed to show is that the whole query model is really more general, the inductiveness query model. It is more powerful. And the way in which we did it is that we showed that there exists a class of transition systems, call it P here, such that there is an algorithm, an inference algorithm in the whole query model that can infer invariance for these transition systems with only a polynomial number of queries. Whereas if we look at the inductiveness query model, then any algorithm in that model will require an exponential number of queries in the worst case to learn invariance for this class. And I do want to describe this class of transition systems shortly. So the class of transition system consists of maximal transition systems for monotone DNF formulas with n terms. So first, monotone, we already said, monotone DNF means that the variables only appear positively. Here is an example. Here phi is just, it has two terms, x1 or x2 and x3, and you see all variables appear positively, so it's a monotone DNF formula. And when I talk about maximal transition system for some formula, what I mean is that these are transition systems that includes all the transitions except the ones that violate inductiveness of phi. So there will be a transition between any state satisfying phi and any other state satisfying phi, and there will be a transition between any state violating phi and any state violating phi. So all of these transitions, for example, and transitions from state violating phi to state satisfying phi. The only transitions that we don't have are transitions going from state satisfying phi to states violating phi. Okay, so it's maximal in the sense that any transition that we would add would destroy the property that phi is an inductive invariant. Okay, so this is the class of systems. Maximal transition systems for monotone DNF formulas. And let me now convince you that that when I think about the whole query model, there exists an algorithm that can infer invariance for this class of systems with a polynomial number of queries. And actually, we saw this algorithm. The interpolation algorithm that we saw earlier if I just take my parameter k to be 1, this will already manage to find the inductive invariant for these transition systems. Essentially, what will happen is that in every iteration where we find some counterexample to induction and generalize it, we will learn or infer one term in the inductive invariant. And the reason is that when we do our generalization by dropping literals and checking that after generalization we cannot reach a bad state in one step, then what will happen here, this ensures that we always stay inside phi. Because we know that in this specific kind of transition system, everything that is outside of phi can reach bed in one step. So this means that during generalization, we will always have sigma prime that still implies phi. It is still under phi. This is one thing. And we drop literals iteratively as long as we can. So we get a minimal term that still implies phi. Or in other words, this is a prime implicant of phi. And remember that we are looking at transition systems for formulas that are monotone. So for monotone formulas, we have the property that every prime implicant is a term in the formula. And this is why in every iteration, we will basically learn a prime implicant, which is a term in the invariant. And this means that if we have n terms, it will take us n iterations to find the inductive invariant. And this is an algorithm in the whole query model. We saw it earlier, and I emphasize that we do have this whole query here. Now, what about the inductiveness query model? So here the claim is that talking about maximal transition systems doesn't simplify the problem, and therefore we still need an exponential number of queries to infer invariants even for this class in this model. And the reason is that if we think about some inference algorithm in this model, when it interacts with the oracle, it asks inductiveness queries, and what it gets back is basically, if it gets yes, it's done. If something is inductive, we are done. And otherwise, it gets a counterexample to inductive, which is a transition. So the same run that we had when we looked at some arbitrary transition system with phi as an inductive invariant, the same run also exists when we think of a maximal transition system for phi. Because there we only have more transitions. So every counterexample to induction that we got as a response, we can get here as well. We have the same transitions and more. So this tells us that basically the complexity of learning invariants for maximal systems, the query complexity, the number of queries needed to find the invariants for maximal systems in this model is at least as high as for arbitrary systems. Having maximal system doesn't simplify the problem. And we know that for arbitrary systems, learning monotone or inferring monotone DNF invariants requires at least an exponential number of queries. This is the lower bound that I started from. This is true even in the whole query model, so definitely also in the inductiveness query model, where the queries are more limited. Okay, so this completes the proof of this theorem. So we have this class of transition systems where we have this exponential gap between the two models. And this is interesting because, so I showed the upper bound using the interpolation-based algorithm, but we could use also a very simple variant or simple case of IC3. And the reason why this was really interesting to me is that a few years back, I had a paper where, with Ari Gorfinkel and Yakir Wiesel, where we actually wanted to describe IC3 as an instance of ICE, as an instance of basically the inductive query model. And when we tried to do it, we sort of saw that we need some extension. So we just extended. But here, in this result now, we have a formal justification for this extension. It's actually needed. There is a real gap between the two models. Okay, so this is what I wanted to say about the complexity of these two query models. And now I want to go back and compare what we saw to what we know about concept learning. So this is what we just said about invariant inference with queries. We said that, that if we are thinking about inferring monotone DNF, short monotone DNF formulas, that in the inductiveness query model for maximal systems, we have basically in the inductiveness query model, we have a lower bound of an exponential number of queries regardless of whether we talk about arbitrary transition systems or maximal. But in the whole query model, we know that for maximal transition system, we can infer them with polynomial number of queries, and for general systems, we have a lower bound, which is exponential. Now, if we look at what is known in the literature of exact concept learning for learning monotone DNF formulas, so there, if we think about a model where we only allow equivalence queries, then the query complexity there is sub-exponential. And if we allow both equivalence and membership queries, then we can learn monotone DNF formulas in a polynomial number of queries. So now if we compare the two things, so if I put the inductiveness query model side by side with the equivalence query model, because they do sort of, they seem similar, right? Equivalence, you just say, is this the candidate? Inductiveness, you ask, is it inductive? They seem similar, but we see that there is actually a gap in the query complexity that we need, because in the inductiveness query model, we need an exponential number of queries to learn monotone DNF, whereas if we could ask equivalence queries, we could do it with less. And we can ask ourselves why, what is the difference? And the difference is really in the counterexamples. When we talk about the equivalence model in learning, there, if a candidate is not correct, then what we get is a positive or negative example, which means that the learner at every point in time has a set of negative and positive examples, and based on these two sets, it needs to come up with a candidate. When you think about the inductiveness query model, like we said, what we get from the subsolver is just a transition that gives us an implication example. It tells us if the pre-state satisfies the invariant, the post-state needs to satisfy it as well. Or in other words, in other words, this is sort of a disjunctive example. We don't know for sure if it's positive or negative, we just know that we have this implication. And the difference in complexity basically shows us that learning from counterexample to induction is really harder than learning from positive and negative examples. And again, this is a result that maybe is not surprising. It's an insight that already existed in the ICE framework, but now we can really give it a formal justification by looking at the complexities in this way. And the second thing that we can see here is if we look at the whole query model, which is the more general one, compared to the learning model with equivalence and membership queries, we again see a gap. And this tells us that in general, we cannot implement equivalence and membership queries using whole queries. So this is actually a very sad result, because our goal was to be able to take algorithms and complexity results from concept learning and use them for invariant inference. And this says that in general, we can't do it. And whole queries are not as powerful in a sense. But in the last part of the talk, I want to say that this is not so bad, because we did manage to show that there are cases where we can actually use algorithms and complexity results from concept learning and get from them complexity results and algorithms for invariant inference. And again, the difficulty in doing that is the fact that if we want to take a learning algorithm and use it for invariant inference, we somehow need to implement the oracle, even though we don't have anything that knows the inductive invariant. But what I want to claim or to show you is that we actually already did it. I already showed you an example where we actually did. This is the interpolation-based algorithm that I showed earlier. The algorithm where we start from a candidate false and we iteratively weaken it based on counterexample to induction. And so this infers invariance in DNF. And if we look at an algorithm for exact learning of DNF formulas, so this is what we have here on the left-hand side is an algorithm that goes back to Valiant in 84. And you can see that it looks almost exactly the same. The difference is that here in the learning algorithm, when we had an equivalence query, in our algorithm, we have an inductiveness check. And here in the learning algorithm, when we had a membership query, then in our interpolation-based algorithm, it turned into a bounded a whole query or a bounded model check. So they seem really similar. And this is really interesting because if really the interpolation-based algorithm is an implementation of the learning algorithm for DNF formulas, then it means that whenever the DNF algorithm, the learning algorithm performs efficiently, whenever we have some bounds on its performance, then we can get the same complexity results for inference. But then the question is, when is it correct? When is this really an implementation? When can we do this transformation from concept learning to inference, and when will it be correct? So what we showed a theorem that said that we can, in fact, implement membership and equivalence queries in the whole model or using a SAT solver under two conditions. If the invariant needs to be k-fenced, I'll talk about it in a minute. And we also have some additional condition on the queries that the algorithm asks. So we call it one-sided. This is a sort of technical condition. I have it on the slide, but I'm going to skip it. So we have some condition on the specific queries that the algorithm can ask. But let me now tell you what is this more interesting condition, which is the invariant being k-fenced. So k-fenced invariant, an invariant is k-fenced if all the states in its outer boundary can reach a bad state in at most k steps. So the outer boundary of an invariant consists of all the states that are outside of the invariant, but they differ from some state inside the invariant by just one bit. So for example, here, if I think of I star here as my invariant, it consists here of only one state, 0, 0, 0, then these are the states in the outer boundary. And the fence condition, the k-fence condition holds for this if all these three states can reach a bad state in k steps. So note that I don't require that all the states outside of the invariant reach a bad state in k steps, only the ones on the outer bound. And if we think for a minute back to the example that we had at the beginning with this n-bit vector that is increased by an even number in every step, and this was the inductive invariant that we had. So we can see that the outer boundary here is exactly all the odd states, and all of them can really reach a bad state in one step. So this is an example of an invariant that is one fence. But this is actually the degenerate case, because in this specific case, the boundary actually consists of the complement. So it's not really interesting. Still, I wanted to show. Okay, so this is the condition of being k-fenced. And again, so what we showed is that if that we can take an exact learning algorithm, and we can, and if this algorithm uses one-sided queries, then we can transform it into an inference algorithm that can infer k-fenced inductive invariant. That's basically what we got. And as a corollary, so and then we saw that this kind of transformation, it actually applies to the algorithm for learning monotone DNF formulas. So using this theorem as a corollary, we could derive efficient inference of k-fenced invariants for monotone DNF formulas just by taking an existing algorithm. And actually, when we do this transformation, we get the interpolation-based algorithm. So you can say that basically we could rediscover the interpolation-based algorithm that was proposed completely independently just by thinking a transformation from an existing algorithm for learning DNF formulas. And we can, once we have this theorem, we can also apply it to an algorithm for learning almost monotone DNF formulas that was proposed by Bishuti in 95. And again, we can take this algorithm and get from it an efficient inference algorithm for k-fenced invariants in almost monotone DNF. Almost monotone means that now we do allow some negated variables, but they can only exist in a constant number of terms. Okay, so this was actually nice. In verification, we don't have an algorithm for learning or for inferring almost monotone DNF. So this is actually a new algorithm that we can get that we can now use in verification, and we have a complexity result for it because it is efficient, provided that the K-fence condition holds. And then the next question that came to mind, so in Bashuti's paper, he also has a very nice result showing that you can learn using this model of equivalence and membership pairs, you can learn also formulas that have both a short DNF and a short CNF representation. An example of such formulas are formulas that have a short decision tree. And this is a very nice result. So we asked ourselves, can we take this algorithm, the CDNF algorithm, and apply the same transformation on it to get, again, inference of such inductive invariance efficiently, provided that we have the K-fence condition. But unfortunately, the answer was no, because this algorithm, the Bashuti's CDNF algorithm, doesn't use the kind of queries that we require. It doesn't admit the restriction that we have. Its queries are not one-sided. So we can fix it a little bit by extending. So we extended our theorem, and we showed that if we remove the requirement of the queries being one-sided, we can still implement membership and equivalence queries, but then we need to require a stronger condition from the invariant. It needs to be two-sided K-fence. I will not get into the details, but this is really much nicer. So we weren't very happy with it. And then actually in a subsequent, so this is the corollary, that we can have efficient inference of CDNF invariance if we have the two-sided K-fence condition, which is stronger. But again, we weren't very happy with it. So then we managed to show that actually we can still get efficient inference of CDNF invariance, even if we only have the K-fence condition, the one-sided one. But this result now wasn't by transformation from learning. So still we were inspired by learning, but we cannot say that this was just taking the CDNF algorithm and doing this transformation. But still, overall, we do get the result that we can infer CDNF invariance provided that the K-fence condition holds. And that's it. So I just conclude, and what I described in this talk and in this kind of work, we wanted to really compare SAT-based invariant inference and exact concept learning. So the first thing that we did was look at invariant inference as a sort of learning with queries, and we defined two query models for doing so, the inductiveness query model and the Hoare query model. We show that they do capture a lot of the SAT-based algorithms out there. We showed some complexity results. In particular, we showed there is a gap between the two models, which reveals a gap sort of between ICE and IC3. We showed that inference is in some sense harder than exact concept learning. But we also showed that under certain conditions, the fence condition, basically, we can take algorithms from learning and transform them into algorithms for inference and get the same complexity results. That's it. Thank you.
Is it on? Okay. Yeah, thanks, Sharon, for that excellent talk. There are questions from the audience.
Yeah, Sharon. You said the invariants that you're learning, they are in DNF. But all these model checking algorithms, they usually learn it in CNF. Like IC3 PDR. So what am I missing there?
So first interpolation does work with DNF. It does generate disjunctions. Yeah, when you have to turn to the SAT solver, you will convert to CNF. But also, so a lot of the results also hold for CNF. So I use DNF because I wanted to talk about interpolation, for which we have these also nice complexity results. But for example, when I showed the gap between the two query models, I could also obtain the upper bound using a variant of IC3 that infers CNF formulas, CNF invariants, and then we still have the same gap. So if I think of IC3, this can also be my candidate for providing the upper bound for the whole query model when I show the gap. So yeah, it's just so we didn't. If you ask, so we didn't find. I'm not saying that it doesn't exist, but we looked at from the learning perspective. We looked at algorithms for learning DNF, and that's. I mean, yeah, and that's. And therefore, we also considered algorithms for inference that do the same thing. But a lot of the results, you could also you could just do sort of dualization and they would transfer.
Thanks. Yeah, you start with init and then generalize it. So if you had started with say bad, not of bad, and then kind of strengthened it, right? So then would you have solved inductiveness query? I mean, like IC3, but you do not do the pushing. I mean, you do not compute the pre-image computation.
I'm not sure I understand. So I could, in the whole query model, we could also model an algorithm that starts from not bad and strengthens. Actually, this would be really we can do it also in the, well, depending on what exactly we do. If we just, start from not bad, check inductiveness, get the counterexample to induction, and then strengthen based on it, then this is an algorithm in the inductiveness query model. This is like doing sort of the dual of backward reachability. But if we wanted to do something a bit more sophisticated, which is when we strengthen a bit more, like IC3, then probably we wanted to do something like a whole query. Right? We wanted to somehow, like if you in IC3, you check some relative inductiveness relative to a different frame. So this would require a whole query. Does it answer the question? I'm not sure I understood.
No, I'm asking whether do you need whole query in that case? So say you are just strengthening by one state and just check for inductiveness, right? So then you can model it in the inductiveness query itself, right? So does it change complexity in that case?
Yeah, so you're right. If all that I do is strengthen based on one state, then yes, I don't need whole queries. This is an algorithm in the inductiveness query model. So, and which means that in particular, the lower bound that we showed would apply. In the worst case, maybe I should emphasize one thing here about the querying complexity. When we talk about the querying complexity, it is the worst case over all the possible responses that the oracle could give me. So what the lower bound shows us that if I take the algorithm that you propose, just starting from not bad and always strengthening based on one counterexample to induction, then this algorithm, in the worst case, it will have some run where I will need an exponential number of queries before I converge. Because basically, I have to somehow discover the transitions sort of one by one, or I don't know if I have a good way to give the intuition, but the lower bound will apply to that algorithm as well.
I have a couple of questions. So firstly, in the generalized step in your algorithm, when you add a point, you check using bounded model checking if the bad states are reachable from that point within k steps. But it is possible for a bad state to be reachable within more than k steps, right? So and if you add such points, your inductive invariant may not necessarily be disjoint from the set of bad states later on. So how do you ensure that this is not the case?
Yeah. So I sort of skipped over this detail, but I did say, so this is the case where the algorithm would fail. Remember that I said that k is a parameter. So if at some point I generalize too much, exactly in the sense that you said, just because I checked k steps, but I added a state that can reach a bad state in k plus 1 steps, and I just didn't know. So this is the case where in the next iteration, my bounded model check there would tell me that I failed. So in real, when you use interpolation, what you do is usually if you get to this situation, you fail, you just increase k. And this is also what we have in mind. But for the analysis, we said, okay, now k is a parameter, so either we succeed or we fail. And in the case, in the example that you decide to just fail. Okay, but again, the idea is that you would use this iteratively with increasing case. And another thing to note is that we do have a guarantee that if the K, if there is, so this is basically the result that I showed later, that if there is a K-fenced invariant, and K-fenced only requires for a certain set of states to reach bed in beds in K steps, not for all the states outside of the invariant, just the boundary. So if there exists an invariant that has this property, then we have a guarantee that the interpolation-based algorithm with this K will not fail. It will succeed and it will converge to an inductive invariant, and we can even guarantee that it will do it efficiently depending on now whether there is whether the invariant is a monotone DNF and so on. So this is an important point. This is basically the K-fence condition, at least for the interpolation-based algorithm, guarantees that we will not fail.
Okay, and the other question I had was, throughout this talk, you were considering only short invariants, right? Which are polynomial in the size of the problem. So do you know of any transition systems where no such short invariants exist?
Yeah, you can think of such examples. I don't have one in mind, but yes, but I think that for those, I don't know if we have good hope. I mean, maybe we can verify them without finding an explicit inductive invariant, but if the inductive invariant itself is exponential, or if the shortest representation is exponential, then I don't think we have much hope. This is why we focus now here in our problem definition. We basically focused on cases where there is an inductive invariant that is short, or we ask whether we can learn a short inductive invariant.
Yeah, but so there are examples where where a short invariant does not exist, right? So have you found
but,
them?
No, I mean, I'm sure that there are, but I'm saying that we didn't really, I don't have like an example in mind, and I don't know if any of the transition systems that we encounter in practice will be like that. I sort of think that not, that probably in realistic cases, we will have short inductive invariants, but I don't have a good answer because, yeah, I'm sure, I mean, you can definitely construct a synthetic example like that. I'm sure, but I don't have an example in mind.
Okay, thank you.
Okay, any other questions? So Sharon, I had one question, which was, most of your work is about Boolean transition systems. And typically we want to find invariants for programs. What do your results apply to the setting of programs?
Yes, this is a great question. And actually, I'm usually also, when I develop algorithms and in my work, I usually actually consider infinite state systems and systems modeled using first order logic. So there is a simple answer here first, that these Boolean systems that we consider, they could come from predicate abstraction. So this is one way in which this actually does address infinite state verification if every Boolean variable represents some predicate. But then the more interesting question is whether we can really extend it to algorithms that really operate in a richer logic. For example, first order logic, quantifiers, theories. So this would need an extension. I mean, I'm not sure. I mean, it's really interesting. So we did try to look a little bit at learning algorithms for quantified formulas. But the literature there is learning with queries of quantified formulas, but there is less literature on that, and we didn't pursue it enough to say anything smart. So I don't have results on that, but I think this could be really interesting to see if we can take such algorithms for learning quantified invariants and turn them into algorithms of inference. So I don't have, we haven't done that, but I think it's really interesting, and that is something that I hope someone will do, maybe us.
Okay, any other questions? Okay, so thank you, Sharon, for a great talk. Thanks for joining.
Thank you, and enjoy India, so that I can't be there.
Yeah, we missed having you here in person.
Thank you. Bye-bye.
Ritik.
Oh, yeah. There you go. Are you using the clicker?
Yeah.
Yeah, welcome back everyone for the last session of today. We're happy to have Kavita Delikabari, who will be talking about maximum popular matchings.
Yeah. Thanks. This is joint work with Kaz Makino from RIMS Kyoto. So this is a problem in the domain of matchings under preferences. Our input is a bipartite graph, as shown in this figure, where every vertex has a strict ranking of its neighbors. So these numbers on edges, 1, 2, 3, so forth, they denote the ranks. So 1 is a top choice neighbor, 2 is a second choice neighbor, and so on. This is an extremely well-studied model used in several real-world problems, such as matching students to schools or colleges, medical residents to hospitals, and so on. Our goal is to find a maximum matching that's optimal with respect to these ranks or preferences. So we still are yet to define what it means for a matching to be optimal. The classical notion of optimality in this setting is stability. A matching is stable if there is no edge that blocks it. An edge AB is said to block a matching if both A and B prefer each other to their respective assignments in the matching. So let's look at an example. We can easily check that the red matching is stable. There's no edge that blocks it, while the blue matching is unstable. The edge between the two middle vertices blocks it. They would rather be matched to each other than to their current partners. So the famous result of Gale and Shapley from 1962 tells us that stable matchings always exist in such a bipartite graph, and they gave a simple linear time algorithm to find one. So in all the applications that we discussed a couple of slides ago, vertices on one side of the bipartite graph, that is schools or colleges or hospitals, have capacities. So what we really seek in these applications is a many-to-one matching. So for those who attended Vazirani's talk in the morning, a B matching. So what we want, so such an instance is also referred to in this domain as a hospital's residence instance. So we're given a hospital's residence instance, and we want a subset of the edge set such that every resident has, as usual, at most one edge incident to it, but hospitals can have multiple edges incident to them. More precisely, every hospital edge has up to capacity of edge, many edges incident to it, where capacity of each hospital is also a part of our input. Is this okay? Oh my God. Okay. You got him in. Thanks. So in fact, Gale and Shapley in their paper showed that their algorithm extends to this many-to-one setting or the hospital's residence setting. So corresponding to any hospital's residence instance G, there is a corresponding one-to-one matching instance. These are called marriage instances, where every hospital is replaced by capacity of H many clones. So every clone has capacity 1, and its preference list is exactly the same as the hospital H preference list. So let's look at a small example. There are 2 residents R and R prime, 2 hospitals H and H prime, where H has capacity 2. So in the corresponding 1-to-1 matching instance, H is replaced by 2 hospitals, H1 and H2, since it has capacity 2. And every resident just replaces the occurrence of H in its preference list with H1 followed by H2. So as given in this example. So M being a stable matching in the original instance G is equivalent to saying this particular realization of M prime spelled out here, is a stable matching in this marriage instance. So stable matching problems in the hospital's residence instance just translate to equivalent stable matching problems in the corresponding marriage instance. So all looks good, except that the size of a stable matching need not be of maximum cardinality. So in this simple example, where R prime and H are each other's top choice neighbors, the only stable matching has size 1, while a maximum cardinality matching has size 2. There could be exponentially many stable matchings. However, all of them have the same size. That's called the rural hospitals theorem, which in fact says that the subset of residents matched in any stable matching is the same. So the notion of forbidding blocking edges hurts the size of our matching. Recall that we wanted a maximum matching, and that's indeed the case in the applications that we discussed. In fact, we would like to match every medical student to a hospital for their residency, and of course, matching doctors to hospitals in a pandemic. There are many applications where the cardinality of the matching is more important than vertex preferences. So our goal in these problems is to find a best maximum matching. We do not want to compromise on the size of our matching. Well, that itself rules out that a stable matching is our solution, because a stable matching need not be a maximum cardinality matching. So natural relaxation is to ask for a maximum matching with the least number of blocking edges. So this problem was considered several years ago by this group in Glasgow, who showed that finding a maximum matching with the least number of blocking edges is NP hard. So how about other notions or other relaxations of stability? So let's compare any pair of maximum matchings by holding an election between them where vertices are voters. So every vertex looks at its partner in the red matching and its partner in the blue matching in this election between the red and blue matchings, and casts a vote for whichever matching gives it a better partner. And if both the matchings give it the same partner, it just abstains from voting. So let's run this election. The top 2 vertices abstain from voting. The 2 middle vertices prefer the red matching, and the 2 bottom vertices prefer the blue matching. So it's 2 versus 2 in this red versus blue election. This is a tie. So let's consider an election between the red and green matchings. So the red matching wins this election. It wins 4 votes versus the green matching winning just 2 votes. So let's call a maximum matching a popular maximum matching if it does not lose an election against a maximum matching. It's okay, it could lose elections against smaller matchings, but as long as it doesn't lose an election against a maximum matching, we are happy. Since we're interested only in maximum matchings, we're only comparing pairs of maximum matchings. Is this okay? So such a matching need not be popular. It's just popular within the set of maximum matchings. Does such a matching always exist? But let's also recall that we are in the hospital's residence setting. This is how a resident casts a vote. It just compares its partner in one matching with the partner in the other matching. How about hospitals? Things look a little more complicated here because a hospital gets matched to a subset of residents. So suppose the hospital H has capacity 3, and in the first matching M, it gets matched to peak R and S, and in the second matching N, it gets matched to Q, R, and T, where its ranking or preference order is as given on the screen. So how does H vote for this particular 3 set versus the other 3 set? So let's choose a bijection after weeding out common elements. So the resident R is a common element in both the three sets. So that gets thrown out. And the two set PS gets compared with the two set QT via this bijection psi. So every element that is P and S, each of them gets compared with its image under this bijection. And the number of wins minus the number of losses is the vote of hospital H for the first matching versus the second. And how do we choose this bijection? So we'll borrow this notion proposed in the joint work with Florian Brandl a while ago. Let's choose the bijection that is, in fact, going to minimize the hospital's H vote for M versus N. So we're being very adversarial towards M. For M to be popular, in fact, we're going to make it extremely hard. So let's compare P with T and S with Q. So since P is better than T and S is worse than Q, the vote of hospital H for M versus N is 1 minus 1, 0. So this is the worst way of comparing these two sets, and that gives H a vote of 0 for M versus N. So for every vertex V, let's just count its vote in this manner. For residents, it's straightforward. For hospitals, it's via this bijection. And the two matchings are compared by just summing up the votes of all vertices. And a maximum matching is a popular maximum matching if it never loses an election against any maximum matching. So is this okay? So now we should ask, in fact, the question I asked a while ago, does such a matching always exist? So in the one-to-one setting, we showed a while ago that indeed such a popular maximum matching always exists. And there is a polynomial time algorithm to find one. And in fact, it's straightforward to extend all these results to the hospital's residence setting, the many-to-one setting. There's a straightforward natural map from the set of popular maximum matchings in the one-to-one instance G prime to the set of popular maximum matchings in G, where we replace every clone by the original hospital. So finding any popular maximum matching is easy. Our problem is we have a cost function on the edge set, and we want to find a min cost popular maximum matching in fact, the original problem was many to many, but for now, let's restrict our attention to the many to one setting. So the Gale-Shapley algorithm finds a stable matching for us, but there's a lot of work on finding fair stable matchings, that is egalitarian stable matchings, min regret stable matchings, min cost stable matchings. So one is not happy just finding any popular maximum matching in the same spirit. We would like to find a nice popular maximum matching. And an algorithm for the min cost popular maximum matching problem can solve all these variants. So we have some forced edges. We would like certain doctors to be matched to only specific hospitals, or we want to forbid certain residents from getting matched to certain hospitals. Or when edges have utilities, we would like to find a popular maximum matching with the highest utility. Or indeed, we want to minimize the worst rank of a hospital that any resident gets matched to. All these problems are captured via an appropriate cost function. And by solving the min cost popular maximum matching problem, we can solve all these problems. So going back to the one-to-one setting, a couple of years ago, we had a polynomial time algorithm to find a min cost popular maximum matching. So the question is, does this generalize to the many-to-one setting or the B matching setting? So let's recall this straightforward natural map we said from the set of popular maximum matchings in the corresponding one-to-one matching instance to the set of popular maximum matchings in the many-to-one matching instance, where every clone gets replaced by the original hospital. The problem is this function need not be surjective. So by running this algorithm for the min cost popular maximum matching problem in the one-to-one setting in G prime, we need not necessarily find a min cost popular maximum matching in the many-to-one matching instance G. So an example that shows F is not surjective is this. It's a very simple example where there are two residents and two hospitals. One of the hospitals has capacity 2, the other has capacity 1. And say the preferences are as follows. So each of the residents considers H prime to be a better hospital than H, and each of the hospitals considers R to be a better resident than S. So this particular matching where R gets matched to H and S gets matched to H prime is a popular maximum matching in G. So in such a small instance, we could just verify it. But each of the realizations of M as a matching in the one-to-one matching instance, each of these is unpopular. In fact, M prime is more popular than M double prime, and we can show this matching N to be more popular than M prime. So neither realization is a popular maximum matching in G prime. So F need not be surjective. So our result is, if G admits a perfect matching, then F is surjective. So our hope was to solve a min-cost popular maximum matching this problem in polynomial time. We do not know the complexity of this problem, but a min-cost popular perfect matching. So whenever G admits a perfect matching, we know how to solve this problem in polynomial time. So let's again recall, we defined this matching G prime, and we defined this matching, let's call this the canonical realization of M in G prime, where each of the clones of H gets matched as per its subscript to its partner. So H1 gets matched to the best partner of H in M, H2 gets matched to the second best partner of H in M, and so on and so forth. And M prime sort of took the role of M in the world of stability. We said M is stable in G if and only if M prime is stable in G prime. In the world of popular matchings, things become, more messy, and M prime need not be, even if M is a popular perfect matching in G, M prime need not be a popular perfect matching in G prime. So this is an example that illustrates this. So we have 3 residents, 2 hospitals, one of them has capacity 2. So there is a perfect matching here. And in particular, M is a popular perfect matching in the many-to-one matching instance. But the canonical realization of it, M prime, is not a popular perfect matching. But there is some other realization where the best partner of H, that is P, gets matched to H2 rather than H1, and R, its second best partner, gets matched to H1. So one seems to have to juggle these clones, which clone gets matched to which resident, and the whole problem is, how do we find this permutation? So we said, even if M is a popular perfect matching in G, its canonical realization M prime need not be a popular perfect matching in G prime. Nevertheless, M prime is a popular perfect matching in a subgraph of G prime. Let's call this subgraph G prime sub M. The edge set of G prime M is defined as follows. So maybe I should use these points. So for any edge not in the matching, all the copies of the edge are in E prime M. And for each edge in the matching, exactly one copy, the one in M prime, is in this edge set. So the whole messiness was being caused by a resident being promoted from one clone to another, from H2 to H1. These are not real promotions in the many-to-one matching setting, but these are all promotions in the one-to-one matching setting. So that's what was really causing us problems. So this subgraph is eliminating all such redundant edges, and it says if resident R is being matched to H in the matching M, then in the smaller graph, there are no options of R is adjacent to both HI and HJ. It's adjacent to exactly one clone. So we eliminate the problem of these false promotions by restricting our attention to the subgraph of G prime. So how do we use this fact that M prime is a popular perfect matching in the subgraph G prime? So in this previous result I discussed, where there was a min-cost popular maximum matching algorithm given, this algorithm used this notion of dual certificate. So M prime has a dual certificate in this subgraph G prime M because it's a popular perfect matching in that subgraph. So how does this dual certificate look like? For that, maybe this looks a little not so readable. We come up with an appropriate edge weight function, weight subscript M prime, such that for any perfect matching N, its weight under this edge weight function is exactly the difference in the number of votes between N and M prime in their head-to-head election. So more precisely, M prime is a popular perfect matching in G prime M if and only if every perfect matching in this graph has weight at most 0 under this edge weight function. So this immediately tells us that this LP will be useful to us. This is just the max weight perfect matching LP in this graph G prime M. Let's look at the dual LP. So these alpha sub V's are the dual variables. So the constraints just say every edge has to be covered. The sum of alpha values of its endpoints should be at least weight of the edge. And M prime is a popular perfect matching in G prime is equivalent to saying the optimal value of the dual LP is 0. So this is really the dual certificate for M prime in G prime M. There exists a dual feasible solution alpha such that sum of all the alpha values is 0 and every resident gets an alpha value in this set 0, -2, -4, so on and so forth. And every clone of a hospital, HI, gets an alpha value in the positive or in the non-negative set 0, 2, 4, so on and so forth. So a vector alpha that satisfies these three properties along with the dual LP constraints, these edge covering constraints, is a dual certificate for M prime in G prime M. A more convenient way to think of this dual certificate is via this colorful graph. So this colorful graph G star M is essentially the same as G prime M, except that every edge has n parallel copies. It's a multi-graph. So let's give a different color to each copy of an edge. So let's call the red color as color 0, blue color as color 1. So for any resident, any red edge or color 0 edge is preferred to any blue edge or color 1 edge, so on and so forth. And for any hospital or clone of a hospital, it's the other way around. Any cyan colored edge is better than any magenta colored edge, so on and so forth. And then red comes at the very end. And within any color class, every vertex maintains its original preference order. So corresponding to our matching M prime, there is a colorful matching S sub alpha in this multi-graph, which can be constructed as given here. For every edge in this matching M prime, look at the alpha value of the resident. If it's -2j, then give the edge RHI color J. So what we showed in that earlier paper was this colorful matching is stable in this multi-graph. So we're back in the world of stable matchings. And in fact, this was what was used to solve the min-cost popular maximum matching in the one-to-one setting, because we know how to find a min-cost stable matching. So this is as far as G star M is concerned, which was the multi-graph corresponding to G prime M. However, we need to work with the colorful graph corresponding to G prime. And this matching S alpha, though it's stable in the multi-graph G star M, it need not be stable in the larger graph G star. And what we seek is a stable matching in this larger graph G star. That would correspond to a popular perfect matching in G prime via this LP duality. So our problem is to show a stable matching in the large colorful graph G star such that this stable matching corresponds to a realization of our popular perfect matching M. Then by just ignoring the colors, what we get will be a popular perfect matching in G prime. And this would be the pre-image of M under the natural map F. So M prime could have several dual certificates in G prime M. Let's look at that dual certificate that minimizes the sum of the alpha values of all hospitals in H prime. So the fact that we've chosen alpha to be this helpful dual certificate enables us to show this lemma, which says that all the edges incident to the various clones of H are either colored the same or they belong to two adjacent color classes, that is C and C+1. So for any hospital H, either all the edges incident to its clones are in the same color or in two consecutive colors. Suppose K prime edges are in color C and K minus K prime. So K is the capacity of hospital H, are in color C+1. then we can also show that the first k prime clones of H, that is H1 to Hk prime, are matched to the top k prime partners of H in this matching M. So if you recall, my talk put the dog to sleep. So if you recall, R1, R2, so on have been indexed based on the preference order of H on its partners in M. So R1 is its most favorite partner, R2 is its second most preferred partner in the matching M, so on and so forth. And the K prime most preferred partners of H in the matching M get matched to the top K prime clones, let's call it, of H, and the remaining ones get matched again in the same order. So if all the edges incident to these clones are in the same color, then in fact S alpha would be a stable matching in this larger colorful graph G star. However, if the edges are in two colors, C, C+1, then this would have a blocking edge in G star. So in fact, more precisely, if you recall, all hospitals like higher colors to lower colors. So HI would prefer the blue edge RJ, HJ to the edge incident to it in S alpha, which is the red edge. And any resident prefers a lower subscript clone of a hospital to a higher subscript clone. So the blue edge RJ, HI, that is the one in the diagonal edge, would block this matching in the large colorful graph. So this tells us how to permute, how to juggle around with the clones of the hospital. So let's replace this order with, so in fact, yeah, so as I've said here, the top K minus K prime clones of H would get matched along blue edges. So they would get promoted to the higher level. They would be matched along blue edges, and the worst clones would be demoted to the red edges. And it's easy to show that now no edge of the form Ri blocks the resulting matching. And doing this step, so juggling around these clones for every hospital would yield a stable matching in the large colorful graph. And so we get a pre-image of M under F. So basically by running the min-cost popular perfect matching in the one-to-one matching instance, we indeed solve the min-cost popular perfect matching problem in the many-to-one matching instance. So let me quickly show that this approach, in fact, the same thing just taken as a black box, generalizes to the many-to-many matching setting. So now vertices on both sides have capacities, and there's an analogous one-to-one matching instance G prime. So as before, we show the mapping from the set of popular perfect matchings in G prime is a surjective map. And we use our result for hospitals residence instances. We use it twice to prove this. So maybe I just convert soon, right? So sorry. So let's in fact use the result first for hospitals. So we show that M has a realization as a popular perfect matching in some graph G double prime, where all the edges of E prime M along with some of the missing edges come back, but not all the missing edges. And then we use this result for the hospital's residence instance once more. And then we, in fact, can realize M as a popular perfect matching in the one-to-one matching instance. And so indeed, F is a surjective map. So to conclude, a min-cost popular perfect matching in a many-to-many matching instance can be computed in polynomial time. But what is the complexity of the min-cost popular maximum matching problem in a hospital's residence instance? I do not know the answer. So we used the reduction from the many-to-many matching setting to the one-to-one setting. So we know that doesn't hold for popular maximum matchings. So is there some other method? Is it NP hard? I do not know. Thank you.
You have time for questions.
So when you replace the hospital by the number of capacities it has, so doesn't the problem size become pseudo polynomials? Or
So basically, the number of copies it has is at most the cardinality of the size of the set R.
Okay.
So it's not really pseudo polynomial. And in the many-to-many matching setting also, you can't have a clone of a hospital, two clones of the hospital being matched to two clones of the same resident. So everywhere things are at most the number of vertices.
Any more questions? So I have a question. So when the clones are created for the hospitals, so the ranking among them for the residents, they all have to be the same ranking?
Yes, yes. So at least that's how it is conventionally done. So they say H1 better than H2, just all of them follow the same order. Maybe if you do it differently, there is something, but I do not know.
Is the perfect matching condition like necessary also? If G has a perfect, if G doesn't have a perfect matching, then it does not have the surjective function.
I'm sorry, you mean to say if for any popular maximum non-perfect matching instance, you're saying it need not be surjective, it's not surjective?
Yeah, I was asking.
No, I don't think so.
Okay.
So there are some instances where it's not surjective, some instances where.
So is
Exactly. Need not be, it could be surjective too, in which case we know how to solve the problem. So it's in those instances where it's not surjective. So the popular maximum matching instances where it's surjective, the same algorithm, everything else works well.
yeah, but is there a characterization of the surjectiveness?
So there are some popular maximum matching instances where it's surjective, some popular maximum matching problems where it's not surjective, and let's say all of them do not admit perfect matchings. So among those instances that do not admit perfect matchings, in some instances it could be surjective, in some instances it need not be surjective. So there is no characterization that if it's not perfect, then it's not surjective.
Yeah, and if like one of the hospitals had capacity 0 or something like that, but the students still have preferences over the hospital.
No, we could just weed it out because it's not willing to accept anyone.
So it does not count in the perfect matching also, right? Like we'll not.
Yeah. Sure.
Okay, let's thank the speaker again. Okay with recording the talk? Are you okay with recording the talk? Yes.
Yes, sir. Thanks. This is
again.
Yeah.
Okay. Yeah. So next talk is by Ori, and he'll be talking about listing 4 cycles.
Thank you. Okay, so unfortunately, the dog was just expelled, so I'm going to give the talk instead of him. And this is a joint work with Amir Aboud and Ron Sapir from the Weizmann Institute and Seri Khoury from Berkeley. Okay, so let's just get into the stuff. First of all, we are interested in undirected graphs, unweighted, with n vertices and n edges. And the object that we are interested in most in this talk is a 4 cycle, which is just a subgraph of 4 cycles that are connected in a cyclic way, like this. We will denote it by C4. And the specific problem that we are interested in is 4-cycle listing. The problem is, given a graph, find all the occurrences of 4 cycles that are in the graph, okay? That are subgraphs that are not necessarily induced in the graph. So for example, if we have the following graph, G, then the output should be these 2 4 cycles, because these are all the 4 cycles in the graph. This problem has a very trivial algorithm, which is just to iterate over all the subsets of 4 vertices in the graph and check if they if they form a 4 cycle. This is an algorithm in time n to the 4th, and in some sense we can say that this is the best running time of this problem, because there are graphs with around n to the 4 cycles, and in order to find them all, we need to spend this time. So this is very trivial, right? But we actually want something more. We want that if a graph doesn't include a lot of 4 cycles, then we want the algorithm to operate fast, which means that we want that the running time will be output sensitive, will be dependent on the number of 4 cycles in the graph. And we'll denote the number of 4 cycles by t for the rest of the talk. So let's think about a better lower bound for this problem. To do that, we'll define the following simpler problem, which is 4-cycle detection, in which we only want to detect whether a graph includes a 4 cycle or not. And it can be easily shown that the running time, if we denote the running time of 4-cycle detection by upper T detection, then the running time of listing should be at least T detection plus the number of 4 cycles, right? Because if we can solve it in better time than T, then, well, it is impossible if we have T 4 cycles. And if we can solve it in better time than upper T detection, then it implies a better running time for the detection problem. And in fact, the running time of 4-cycle detection was studied a lot, and this is the best known running time for the problem, n squared, where the graph is dense, or m to the 4/3 if the graph is sparse. And our result shows that this lower bound is indeed tight, okay? We developed an algorithm that operates in the running time of the detection algorithm plus T, okay? Detection plus T running time. Okay, so this is optimal also from like what I said before, okay? A better running time would imply, yes? I didn't hear. There is a microphone here.
So randomized or deterministic algorithms?
It is randomized, but I don't think it should be hard.
The lower bound, okay.
Be randomized. Yeah. Sorry. It is deterministic algorithm. Okay. Okay, wants to talk? Okay. So this is the first reason that this is optimal, but an even better reason, stronger reason, is that there is a lower bound conditioned on free sum for this problem, which is pretty tight, okay, up to log factors. That means that if we develop a better algorithm, then it refutes the free sum conjecture that claims that the free sum problem takes at least n squared time, or cannot be solved in sub-polynomic time than n squared. Let's start by the simpler algorithm, which solves the problem in n squared plus t, and this algorithm is pretty simple. So notice that a 4 cycle, okay, is actually combined out of two paths, okay? Two paths of length 2. that collide on their endpoints, okay? If we have two paths that collide on their endpoints, then we have a 4 cycle and vice versa. That means that if we find all the 2 paths, we can combine all the 4 cycles out of them. So the algorithm will be just list all the 2 paths and compose all the 4 cycles from them, as I said. And in order to show that the running time of this algorithm is n squared plus t, we will show that the number of 2 paths, which we'll denote by sharp p2, is at most n squared plus t. And in order to see that, first notice that if the number of 2 paths is greater than n squared, then there must be at least one 4 cycle from the pigeonhole principle. And in fact, we can extend it and say that if the number of 2 paths is at least n squared plus x, then there are at least x 4 cycles in the worst case. Okay, so that was the very easy algorithm. And next we will show the algorithm that is better for the sparse case, which is more involved. And its running time is m to the 4/3 plus t. So first of all, let's notice that listing all the 2 paths, as we did before, doesn't suffice us. Why? We can show an counter example. Let's look on the star graph. This graph is m squared 2 paths, roughly m squared, and doesn't include any 4 cycle. Okay, so if we list all the 2 paths, we'll have to pay at least n squared, which is much larger than m to the 4/3. The first idea will be to do a separation of the vertices into low degree and high degree, and solve the problem differently on each combination of these. So let's define a threshold delta. Okay, it will be m to the 3rd, and separate the vertices into 2 sets of low degree vertices that are of lower degree than delta, and all the rest which are the high degree vertices. And we have 4 different types of 2 paths. The first one is a 2 path with a low degree vertex in the middle. And this type of 2 path is simple. We can handle it simply by iterating over all the edges. We have m edges, and checking if the endpoints of the specific edge are of low degree, and if so, iterating over all the neighbors of this vertex. So there are at most delta neighbors, and that in this manner we can iterate over all the 2 paths of that kind in time m delta, which is m to the 4/3, which is okay for us. The second type is also easy. Why? The second type is with all the vertices are high. We can look on the subgraph induced by these vertices. There are at most 2m over delta vertices in that subgraph. And then we run the algorithm that we talked before that actually finds all the 2 paths, and it finds all the 2 paths if in time m to the 4/3 plus t. So this is also all right. The third type looks harder, but actually we don't need him because we're only interested in 4 cycles, right? So if we try to complete these 2 paths into a 4 cycle, we understand that this 4 cycle can also be decomposed into two paths of type 1 with low degree vertex in the middle. And the 4th type looks harder, and indeed it is an harder case. Okay, so let's talk about this case for the rest of the talk and see how we handle it. So first of all, I will break the dream to list all the 2 paths of that kind. We'll show an example in which we have 2 paths of that kind. So the example is very first simple. This is the graph. We have n vertices, low degree vertices on the top, one high degree vertex on the second layer, afterwards n to the 2/3 minus epsilon vertices of also high degree. And in order to make these vertices high degree, we connect a bunch of distinct n to the third plus epsilon low degree vertices to each one of the vertices there on the third layer. In this example, if we look on the LHH two paths that are formed from up down, from the top down, we see that there are m to the 5/3 minus epsilon LHH two paths there, and it is much higher than n to the 4/3 plus t because we don't have any 4 cycle in this example. Okay, so we can't expect to list all the LHH two paths here. Okay, so what can we do? Okay, on the other hand, we can see that LHH two paths are needed. Okay, we can't say something that is similar to the third two path here. Okay, no, it doesn't matter how we complete the. Okay, if we complete the 4 cycle with a higher degree vertex, then we can decompose it into two paths that are okay, that the first is from the first type and the second is from the second type. But if we complete the 4 cycle with a low degree vertex, then no matter how we decompose this 4 cycle, we still have an LHH two path. So it is needed to list LHH two paths. But what can we actually say about this 4 cycle? So this 4 cycle has an interesting symmetry in it. And what we'll do is we will orient all the edges of the graph from low degree to high degree. If we have an edge from U to V and U is of lower degree than V, then we will orient it from U to V. And if we look on this hard 4 cycle, we will see that the orientation from L to H will be in that shape, from L to H. And what will be the orientation between the H vertices? Well, we don't know, but there are 2 cases. And in each case, the cycle can be decomposed into two paths. One, it is an LHH two path, but that is directed from L to H to the second H. And the second is an LLH two path, which is again easy. Okay, it's type 1 two path. Okay, so actually what we really need to do is to list all the directed LHH two paths. Okay. And surprisingly, we can do it. If we denote the number of these two paths by P, the main theorem of our work is that if P is very large, is larger than m to the 4/3, okay, is problematic, then the number of 4 cycles in the graph is at least P, and therefore we can afford ourselves to list all these two paths. And in addition, we need to show that we can actually list all the LHH directed two paths in appropriate time, which is possible. It's not very hard. You can think about it. I won't talk about it here. If you want, you can ask me about it later. Okay, so the conclusion is a 4 cycle listing algorithm in time m to the 4/3 plus t. And now we will concentrate on the main theorem, and I will show the idea of how we proved this theorem. The key tool in order to prove this theorem is a property called supersaturation of 4 cycles in graph. Okay, so let me first talk about a simpler thing, the maximum degree of a 4 cycle free graph. Okay, so if we have a graph without any 4 cycles, then the average degree of the graph is at most square root n. There are at most roughly n to the 1.5 edges in the graph. Okay, this is called the extremal number of a graph without of 4 cycles. Okay, graph that is the most dense graph without any 4 cycles. And interestingly, we can extend this theorem and say that if the density of the graph is above this density, then there are not one 4 cycle, but a lot of 4 cycles, okay? Actually squared, n squared 4 cycles. If the average degree is above square root n, then the number of 4 cycles is at least the average degree to the 4th. Okay, so what we will show is that the graph, okay, has a dense subgraph inside it, and it means that there are a lot of 4 cycles in it. In order to show that, we first reduce the graph into a simpler graph, simplified graph, which holds the following properties. So first, the graph is 3-layered. The first layer is of low degree vertices, and the other 2 layers are high degree vertices. And in addition, the orientation of the edges are already from L to H1 and from H1 to H2. The second property is that each vertex in the middle layer in H1 has the same in degree and the same out degree. Okay, all the vertices have the same in degree and the same out degree in H1. And the third property is that any vertex in H2 has a degree at least 1 as an incoming edge. Okay, so I won't show how we came into that graph. It's not very tough, but if you are interested, again, you can ask me. But if we have that graph, I will show that we can prove the theorem. Okay, what actually we will see is that G prime, which is the subgraph of all the high degree vertices, is of high degree if there are a lot of 2 paths of type LHH. We have 2 cases. In the first case, H1 is larger than H2. And this is a simpler case, okay, in which we know that the average degree of G prime is roughly the out degree of H1, the out. And actually, the number of 2 paths of LHH form in this graph is H1, the size of H1, times the in times the out. And we can see that this is at most m times the average degree of G prime, which means that if P is larger than m to the 4 over 3, then the average degree is at least P to the 1 over 4. And using the supersaturation property, we get that the number of 4 cycles is at least P, as we wanted. Okay? So this is the first case, which is simpler. And the second case, in which H2 is larger than H1, says something more interesting. Here we use the orientation. So if we look on a vertex in H2, we know that the degree of this vertex is at least 1. It has at least 1 incoming edge. And the vertex that has this incoming edge has at least d in degree. That means from the way that we did the orientation, that the degree of this vertex in H2 is at least also d in. And the average degree of G prime is actually H1 over H2 times d out, roughly, which is at least d in because of what I said now. And if we do the algebra, okay, again, we know that P is H1 times d in times d out. We see that if there are a lot of 2 paths, then again, the average degree is at least P to the 1 over 4, which means that the number of 4 cycles is at least P. Okay, so this is the idea of the proof of the theorem. And the last thing that I want to talk about, okay, 2 things that I want to talk about. So first, what happens in the general case of an constant length, even length cycle, constant even length cycle. What do we know about it? So we know the detection running time of it. The known detection running time is the minimum between n squared and m to the 2k over k plus 1, okay, which is a generalization of the running time of 4-cycle detection. And the question is, can we solve C2K listing in this running time, in detection plus T running time for any K? And actually, it is not known. What is known? Okay, so even for the dense case, the n squared plus T algorithm is not known. We believe it is possible. But for example, if we think about 6 cycles, then we would expect that the algorithm will be something like iterate over all the 3 paths and combine 6 cycles out of them. But notice that here it is more involved because in 4 cycles, if we had two paths that collide on the endpoints, then we have a 4 cycle. Here we can have 2 free paths that collide on the endpoints U and W, but collide also in the middle. Okay, so it won't give us a 6 cycle. So it is more involved. But actually, a very new paper shows that for 6 cycles, we can have an n squared plus T algorithm. But we don't know nothing about the sparse case or larger cycles. So this is a very interesting open question, in my opinion. Let me talk a little bit about motivation for this problem, which in our case made me to think about this problem. We were interested in the relation between triangles and 4-cycle problems. So a triangle is just a cycle of length 3. And okay, so I already said that the 4-cycle detection is in this time. Triangle detection seems harder. We know to solve it in n to the omega, when omega is the matrix multiplication constant, or m to the 2 omega over omega plus 1 for sparse cases. Notice that if omega is 2, then these 2 running times are the same. But it seems harder. And we wanted to show a reduction from 4-cycle to triangle detection in order to show that 4-cycle detection is easier than triangle detection. We don't have an idea how to do so. But okay, we want to show a fine-grained reduction between the two, a reduction that is fast enough in order to show that triangle detection is harder. But notice that if the reduction preserves the number of occurrences of cycles, then it must also work for the listing versions of the problems. Okay, so we didn't know if listing 4 cycles can be done faster than triangles. So this is was a barrier for us. And this is what is known for triangle listing. And okay, actually, there are pretty matching lower and upper bounds for this problem. And actually, we showed that we can solve 4-cycle listing in faster time. So it actually shows a separation between the problems and shows that this problem of 4-cycle listing is indeed simpler. And actually, we still have a barrier in the counting versions of the problems. Okay, so counting, we don't know how to solve faster for 4 cycles. It seems harder for 4 cycles. So if someone is interested in it, you are welcome to talk with me about it. So thank you for listening and questions.
Questions?
Oh, okay, interesting question. The question was what is known for larger odd cycles. I don't think it was studied. Like I don't think someone developed an algorithm for that, but we can show a reduction from a triangle listing to these problems, okay? So it is not, it is harder than, at least as hard as triangle listing.
Sorry, this is a silly question, but for the C2K problem, if I said K equals n by 2, is that not just Hamiltonian cycle? What am I?
Right. So I assume that K is a constant.
Okay.
C2K for a constant K.
Just want to do detection that you can always do it like n to the omega k time or something like this.
If the graph is of size K?
That you can always do something like matrix multiplication time. You can so the trivial time would be like n to the k, but you spoke about this algorithm for triangle detection, which runs n to the omega time. So is it can you always get a gain for?
So you are talking about, if I understand correctly, you're talking about an algorithm for detecting a click, right?
A click or some graph on k vertices.
So you're saying that you can in which time?
Yes. So the question is, can you gain over n to the k in general for just detecting the trivial running time would be like n to the k. Can you always get an improvement over this?
If I can always get an improvement over that for any subgraph. Interesting question. I think that yes, I think that there is always, but I'm not sure. Like I think that click is the most hard instance of the problem, and there is an improvement there.
And one other question, so is that this click algorithm really uses graphs. So if you go to like hypergraphs or something, is there any analog of this matrix multiplication type improvement?
I think that no, but I'm really not sure. I think that there is no analog.
So does your algorithm also work for diamond listing? Because the two-path patching, right? It seems to work also for diamonds, which is like C4 plus 1 edge.
If this also works for diamond, okay, actually yes, it is work. It works, like at least the n squared plus t works, right? Because you can just find 4 cycles and each 4 cycle check it. But there can be much.
You have these complicated.
Okay, maybe it doesn't work. I'm not sure. I need to think of it offline.
Yeah, thanks.
Okay.
How about directed graphs? 4 cycles in directed graphs?
Interesting question. In directed graphs, we can actually show a reduction from triangle listing. So it is as hard as triangle listing, and we can solve it also in n to the omega. And also, I think that we can do also the sparse analog of the detection in n to the omega. And I think that we can also do the listing in the same time as listing, but or as triangle listing, but not really sure.
Any more questions? Let's thank the speaker again.
So that brings us to the end of today's talks. We have a business meeting at 5 o'clock. All right. So we have a business meeting at 5 o'clock. You're all welcome to attend. But otherwise, the bus for the banquet leaves around 6, I believe. The announcement that the local organizers made. So yeah, look forward to seeing you at the banquet or the business meeting.
Yes.